Hi friends, welcome back to another session on operating systems. Now let's get into the second module. Hi, I am Dr. Sandeep, your mentor, welcoming you to this second module of this series wherein we look at process management. So what we have in store for the coming sessions is look at the process management, then about the multi-threaded programming, and finally look at how the processes are scheduled. So that's the summary of this part of the series, module 2. So let's jump into the process management. So what process is? Process is a program in execution. We do have programs that are written to serve some purpose using some programming language, and as long as this program is there on the secondary memory, it's just a program, it's a text. It becomes active, live, the moment it is loaded onto the main memory, and once it is in the main memory, then it can be executed by the processor, and hence the program, once it is loaded onto the main memory, it becomes a process. So we can say a program in execution is a process. It forms the basis for all the computation, and a process consists of a code. That's a program. That's a textual part, what we call a program, written in some programming language, is dumped onto the main memory. That's one part. Then we have a program counter. That means which line is under execution currently, because the processor can execute only one instruction at a time. Therefore we need to keep track of which instruction is being executed currently and what is the next instruction to be executed. So the next instruction to be executed is located in some address of the memory. The address of the memory where the next instruction to be executed resides, that address is there in the program counter. So whenever the processor wants to execute, then it looks at the program counter and goes to that location in the main memory shown by the program counter and gets one instruction, executes that. The moment the processor fetches one instruction, automatically the program counter starts showing the next instruction. So that's the purpose of program counter. Then we do have internal registers which are there in the processor. So these help in storing temporarily the intermediate results, the data, so that the manipulation is easily possible. So a set of registers are provided with the processor. So these registers and their contents, and we do have a memory, and memory contains global variables as well as local variables. Then we have a stack. So to store the information whenever we are switching from one process to other process, we just want to remember how much of this process we have executed, and when we come back to the same process, then where to start again. So we need to store the whole environment before switching to another process, and then when we come back to this process, the whole environment is recreated and all that. So for many such issues, we do require data structure called stack. So this all are there along with what we call a heap memory, used to store a set of data that is required for execution, and that's what pictorially we can show. Here what we call text is the code of the program. Then it will contain its own data. When we are working with a program do contain some data. The data is stored in this part of the memory. Then we have a heap memory, then we have a stack. This is what the memory looks like for a process, and there's other things like program counter, contents of registers and all are inside the processor. This is on the main memory, that is the RAM. So here we have the text, that is the code, then associated data, then we have a heap for additional data, then we have a stack. All these are available. The data may contain global variables or may contain the local variables. So issues related to global variables, local variables. This is when we are talking about any program. The program may contain functions. Inside the functions we may define some variables, so they are local to that function. There are some variables which are applicable to all the functions, so such variables we do call that global variables. So we have global variables, we have local variables, all of them will be part of the data. Some, when the size of the data increase and we want to have fast access to data, then we do use a data structure called heap. Then first in first out type of data structure is required in some cases for pushing and popping, so for that we do have stack. So in all, the program, the code which is stored in the form of text in the main memory, associated data, then the variables, then the stack and the heap which are part of the main memory, and program counter and registers and their contents which are there inside the processor. All these together will form what we call a process. So that's the basic about the process. So many issues about the process, its management and all we need to look at. So keep watching. So that's it for now. Thank you. Hi friends, let's continue our journey into the process management of operating system. Under this, first let us see. We began the operating system with something called MS-DOS, disk operating system, which was designed by Microsoft, which was very famous, quite famous, MS-DOS. So in general it was a disk operating system which was meant to process one process at any given time. Therefore it was a single tasking operating system, and anytime only one active program used to run, and the entire CPU was devoted to one process, and the memory was sufficient to accommodate only one process. So there was no chance of accommodating more than one process. During those days, the processor was like a 8086, which was a 16-bit processor having 20 bits of address lines, which maximum could work with 1 megabyte of memory. Of this 1 megabyte memory, 640 kilobyte was reserved for the disk operating system or the operating system, and the remaining 360 kilobyte of memory was available for the usual process. In that only one process could be accommodated. So if we want to run one process, so we just load that process onto the main memory, run it, and once that is done, then want to run another one, then it has to replace the first process from the memory and the second one should get into its place. So that was the day when we were working with a single process any given time. But later, with time, the technology developed, VLSI came in. So 801, 862, 863, 86, Pentium and all that went on improving, and with that the memory on board went on growing exponentially, and with this we could accommodate more than one process at any given time. That means we can load more than one program from the backend onto the main memory at any given time. But since there is only one processor available, so any one of these processes can be made active and all others should be inactive. And this type of working is what we call multitasking. So the multitasking operating systems can run multiple processes simultaneously. That means it can have multiple processes simultaneously on the memory, but anytime only one process will be active, only one process will get the CPU time, all others should be waiting. So the examples were Linux, Windows, Mac OS and all that. So here the CPU is allotted to any of these processes one after other, or as per the user's requirement, and the CPU time is divided between these processes that are active. We see more detail what mean by active process, what do you mean by waiting process and all that. And then we have interrupts. So the interrupts were very limited in case of single tasking operating system, but when it comes to multitasking, we must handle multiple IOs, multiple system and user interrupts were supposed to handle. So we need a little more complicated operating system for doing so. The memory all the memory was allocated to one process in case of single tasking operating system, whereas in multitasking operating system, each process will have its own memory segment from the main memory, and the CPU is allotted on time to time. So that's a difference between single tasking and multitasking. So there is nothing much to talk about single tasking. So from now onwards, we will be working only with the multitasking at its base. So whatever we speak about operating system, it is the minimum facility we are providing is multitasking. So no more single tasking activity, it is multitasking, and then we extend our functionalities beyond that. So that's where we begin our journey with multitasking. So that's all for this session. If you find this session of any use, please don't forget to like, subscribe the channel, and please share with your friends, and have anything to say, please do comment. So that's it for now. Thank you. Hello friends, welcome back. Last session we have seen the difference between single tasking and multitasking, and then we realized that the latest machines have ample resources, a lot of memory, so that it can accommodate more than one process on the main memory, and hence we do consider from multitasking system onwards. Now the issue here is on the main memory, multiple processes are residing, and since there is only one CPU, then any one of these processes can be active and all others must be inactive or some other way. So to define what each one is doing, we need a term called a state, process state. So process state represents the current status of any given process, what the process is doing, and if it is waiting, then what for it is waiting, and all that. Now a process can be in many states. It can be a new state. So whenever a process is created, it gets into something called a new state, and when the process is waiting for the CPU to be assigned, then it is called ready state. And if the processor is assigned to the given process, or if the process is currently being executed on the CPU, then we call that process is in the state of running. Or if the process may be waiting for some slow process, some event that takes quite long time, maybe like waiting for some IO activity or waiting for some resources which takes quite long time, then instead of wasting CPU's time, we can keep this particular process into a deep sleep. So that's what we call a waiting state. And once the work of the process is completed, then it will be going into a terminated state. So it may be completed, that means it ends its execution normally, or something may go wrong, and because of that, instead of creating a chaos in the whole system, we can just kill that process so that remaining things are intact, so it may be terminated abnormally, and so on. So these are the definitions. So a process can be in any of these states, and let us see what exactly happens when a new process is created. That's where the whole thing begins. A new process is created. That means when we press any what I can say, the mouse button is pressed when it is on some icon, then that program which was there on the secondary memory comes over to the main memory, and that becomes a process. So when it becomes a process, it is admitted into our working system, and it gets into a queue where many processes are waiting for their turn to use the CPU to run their code. So it gets into the ready queue, and the scheduler they have something who takes care of how the processes should keep running. So the scheduler will allow a process to run. That means a CPU is allotted to a process. Then when a CPU is allotted to a process, that process is changed its state from ready to running, and the process starts running. The CPU runs that process. So there may be some reason, that means a process may be given some specific time to run, and if that time is done, then it gets interrupted by the scheduler and says that your turn is over, now somebody else has to use the CPU, so please stop your work. So it gets interrupted, and if it gets interrupted and not yet completed its job, then it comes back onto the ready queue and waits for its next turn. So this continues. So process is in the ready state, and if it is the next in the queue, then when the CPU is next available, it is shifted to the running state and starts running, and once its time span is over, then it's interrupted, it gets back to the end of the queue and waits for its next turn. And the next process which is ahead in the queue, ready queue, will now get the chance to run. So that's one cycle keeps repeating. Or a process may be running and it wants to read a data maybe from keyboard. Now what is the problem in reading the data from keyboard? So first problem is the keyboard is operated by human, and human's response time is very slow because mechanical activity has to be taken. So a human may take a few milliseconds to few seconds to work with a keyboard. A key has to be pressed. It is waiting for some key to be pressed, and that information is put on the screen, say that press yes or no. If you want to continue, press Y. If you don't want to continue, press N. Some message is displayed on the screen. The user has to read it, understand it, then decide to press yes or no. If yes, then search for Y. If no, then search for N and then press it. And it's not necessary that the user is active all the time looking at the screen. The user may be busy some other activity and may not be looking at the screen. So in all that, what happens is the time to press yes or no, Y or N, takes some seconds, and the process is running at a nanosecond speed, and if it is taking in terms of seconds, then so many billions of activities we could have done in that, and the processor is wasting all its billions of time stamps just for one key to be pressed, and definitely it is just waste of resources, waste of CPU time and all that. So to ensure that whenever some slow process is initiated, when you are waiting for some slow activity, then instead of waiting for that to happen, we can just transfer the state of the process from running to waiting and say that you please be in the waiting state and wait for the key to be pressed. So it may take some milliseconds, okay, then in milliseconds it will be waiting. It may take few seconds, then for a few seconds it will be waiting, and once that key is pressed, then it is now ready to run again. Till then, don't get back to the ready state, otherwise after a few nanoseconds it will get chance to run again and it says that I did not get the input, so I have to wait. So instead of allotting that process any CPU, just stop that process to claim for any CPU, get that into waiting state, and it will be in the waiting state till that IO or the event has completed. Once that IO event is completed, then it comes back to the ready queue and waits for its turn. So this keeps on going on. So if it is ready to run, then it goes to running state. Then if time's out, comes back to ready state, then gets chance, run, back, ready, and so on. This keeps on. If a specific time slot is allotted for each process, each one should get some equal amount of time for CPU usage. Or if a process is waiting indefinitely for some very slow activity to take place, then better switch to the waiting state and keep it in the waiting state till that event happens. Once that event occurs, then back to the ready state. And while running, if we come across situation where the process comes to an end, then it exits and the process gets terminated, or maybe something goes wrong while running the program, while running the process, something may go wrong. So instead of disturbing whole the environment, whole ecosystem, it is better to kill one process that is creating a problem, so we can forcibly exit and terminate that particular process. So that's what process states are, and this state diagram talks about the story from the time a process is created till the process gets terminated. All these different events occur at different events. The process will be in the different states, and that's what we are talking of. Then how does how do we understand the details? So this whole details about the process are stored under the process control block. There is one block for every process called process control block, where the state of that process is stored, the identity of the process is stored, and the program counter, that means which line currently it is being executed at current state when that is stored. The contents of the registers are stored, the memory limits and other list of files that are open and all are stored. So that all the meta details about process are stored in the process control block. How does this help in our operating system or process control? Let's check that. Say process, we have two processes and one CPU. So currently process P0 is executing, and then it gets some interrupt or some system call, then it has to exit. So it gets out. So before going out, it saves its environment onto the PCB, and then the second process, that is P1, is allotted the CPU. So before process 1 starts working, we should know, has process 1 executed earlier? If so, then what was the condition when it had stopped working? So we reload all the environment from the process control block of process 1 and then start executing. And when this gets another interrupt, then it cannot continue, because it may be waiting for some IO activity to happen, or it may be getting scheduled. So sometime process P0 runs, then sometime process P1 runs, like that. Then once P1's turn is over, then all the environment of process 1 are saved into the PCB1, and then we reload the state from PCB 0, and process P0 continues its execution. So in this, what happens is, when process P0 stopped working, at that time, what was the situation? The situation is in what state the process was, what is its number, how many, at what line it was working, what are the contents of all the registers, and all these details are stored in the process control board. So it saves onto the process control board, and then when P0 has to restart working, instead of beginning from the beginning, instead of starting from the beginning, it wants to continue wherever it had stopped. So wherever it has stopped, who knows that? The process control block knows about the latest information about that process when it was stopped, and the same thing we reload. So that means we get where the process was, that means the program counter, what are the contents of every register, what are the files that were open, and all those details, what was the process at that time, what was the state of the process, all these details are reloaded from the PCB0, and P0 continues to execute. And sometime later, if P1 wants to continue, then P1 will again continue the same way. P0 will stop, saves all the environment into its PCB, then the PCB1 details are reloaded, and process P1 starts its execution. When P1 is being executed, then P0 is in idle state, so P0 is not working, and when P0 is working, then P1 is in idle state, and so on. So either P0 will be working or P1 will be working. In that case, if there are multiple, then one of them will be working and all of them will be in ready state or waiting state depending on the situation. So that's it for now. If you find this information of any use, please like, share, and do comment, and please subscribe to this channel. Thank you. We are into our second module where we are looking at process management. Process is an instance of a computer program that is being executed. The process, when we say, it's a complete program under execution, but we can look into a smaller part of a process, and that is what we call a thread. A thread is the smallest unit of execution within a process, so we can convert or we can divide a process into multiple threads, so that these threads we can work independently on different processors if available, or we can make sure that these are run as if they are different processes. But yes, there is difference, and the difference is as far as a memory space is concerned. So each process will have a separate memory space for that, whereas the threads share the memory space of the process. So process will have a memory space, and all the threads under that process will share the same memory space. For communicating among processes, we require IPC, interprocess communications, which are very slow, but threads within a process can communicate very easily via shared memory, because all the threads within a process share the same memory space. Therefore, a simple shared memory concept can be applied here, and it becomes easy and fast also. Creation, yes, it is heavy for the process, because whenever a process is being created, first we need to look at what is the size of the memory required, what all the components of the memory required, how much memory is required for the code, how much memory is required for the data, how much memory is required for the stack, how much memory is required for the heap, and all that it has to find out, and then accommodate all the memory, reserve the memory for that, and then load the code from the secondary memory down to the primary memory at the allocated place and all that. So it is a heavy duty activity, whereas a thread is a lightweight. When we are creating a thread, we are just not copying anything from the secondary memory, because the whole process is already on the main memory. Only a light changes are required. We will see exactly what is the difference between the process and thread when it comes to the resources required and all that. When it comes to the crash, then one crash does not affect the other process. So if one process is crashed, it doesn't make any difference to other processes. But these threads are under one process, and if one thread fails, definitely the whole process is going to get affected. So that's other difference. So we need to be very careful when it is thread version, because if any thread fails, then the whole process also will fail. So pictorially it gives a better understanding between the process and the thread. The left side is the process, so it contains one thread. That means the whole process is a single whole code is a single unit. So it has got a place for the code, it has got a place for the data, it has got a place for different files used, then it has got registers, contents of the registers, contents of the stack. This whole thing, one set of code, data, files, registers, stack, all are available for a process. But if we use the same process in terms of threads, then there are multiple threads. Then for each thread a separate stack is there, for each thread a separate memory is allocated to have its own register contents. So as we discussed in the previous session, then when the CPU is allotted from one process to another process, then the whole environment is saved. This saving of the environment is done in the memory, and when it comes to a process, we have one set of memory for storing register contents, one set of memory for the stack, whereas when we are talking about multiple threads in a process, then there is one code, there is one data, there is one file. The memory allocated for the code is only one. The same memory allocated for the code is used by all the threads, so they just use the same code. The data is commonly used by all the threads, so that is what we call shared memory. And the files it has opened and all the operations work with the files is commonly used by all the threads. So that's the difference between multiple process and multiple thread. In multiple process, each process will have a separate code, each process will have a separate data, each process will have separate set of files opened, each process will have a space for storing its register contents, each process will have a separate space for storing its stack, as we have seen in the process control block, all these details. But when it comes to multi-threaded process, then there is only one set of code, there is only one set of data, there is only one set of memory allocated for the files, details and all that. But each thread has its own register contents to be stored on the memory, each thread has its own stack. So that's the difference. So when we are trying to work on the same process in the multiple ways, then instead of copying the same code again and again multiple times on the main memory, we can keep one copy of the code and allow many users to use it through the threads. So user 1 may use thread 1, user 2 may use thread 2, user 3 may use thread 3 for the same process. That means when we are working on this, that is the same code will be used, same data will be used. So this part is common for all the threads, whereas each thread has these components differently. So that is what a thread is. More details about process, threads and all in the coming sessions. So as of now, that's an introductory session for what a thread is and how it is different from a process, or a process consists of multiple threads and all that. So that's it for now. Thank you. To have a better picture of what a thread is, let's take an example of a music player. So when we are playing songs on our mobile or a system, then we press the music player icon and the process of music player begins to run. How do we know that the music player has begun its process? Many ways. One, it is visible on the screen. The picture of the musical player opens on the screen. Then some song comes from the speaker, and then we have many other activities that we can take up. And this act, which feels almost effortless, has much more hidden in its background. Various threads are working to ensure that this process of music player runs smoothly, effortlessly, without disturbing. So to make the process work easily, effortlessly, a lot of threads are working hard behind the screen. So one thread is responsible for what is visible here, that is how the music system should look on the screen. So it is responsible for rendering the visual screen. This thread takes control of what is visible on the screen. Another thread may be attending user interface like play, pause, volume, etc. Then each of these operations are further performed by separate threads. So one thread is responsible for playing. So when you say play, what actually happens is the data, which is in the digital form, will be converted into analog form, and then it is given to the speaker. So while doing so, another thread, which is responsible for the volume control, ensures how much is the magnitude of the signal to be generated before getting into the speaker. Then another thread that is responsible for equalizer may vary various frequency component amplitudes and then ensure that appropriate type of music is audible to the ears of the listener the way the listener wants. So how much of high frequency, how much of mid frequency, how much of low frequency components are required. Accordingly, the changes are made. So for each of these, a separate thread may be working for each of the bands, a separate thread may be working, and another thread may be combining all the outcomes. One more thread may be converting all the digital back to analog. One thread may be fetching the content if the contents are available in the backend like a file. So one thread may be fetching the data from the backend or the file, or if we are getting the stream data, then it should be getting from the cloud or internet. So then stream of data will be received by one thread and then converted into packets, and these packets are given to the player thread and so on. So all these works are being done in the background, so a lot of activities keep doing in the background. So just let's look at just one music player, how many activities are parallelly going on in the background. For us it just looks simple, one music player is working, but in reality we can see how many threads are working. One thread is audio playback, which is the core thread, which streams and plays audio smoothly. Then there is another thread which is responsible for file IO. So from the in the background, the thread reads the music files from the disk or the cloud and keeps the data ready before it is required. Then all the data what we are talking about, music data, is usually encoded, and before playing it should be decoded. So the compressed format should be decoded before actually playing it. So usually it may be MP3 or FLAC or AAC formats are used for compression, and before playing it should be plain data, so it has to be decoded. So another thread will be working on decoding the data what we get. Then another data may be busy with the user, what user is trying to interact with. The user wants to play. When the user hits the play button, the audio playback thread should start playing it. When it's paused, it should stop wherever it was stopped, or it may be stop button, then it comes to end of it and all that. Another thread may be busy in rendering the visual effects in the real time, like the visualizer, equalizer. So they are working in real time, so they are rendering the visual effects or even the audio effects. The visualizer is rendering the visual effects, or equalizer is rendering the audio effects in the real time. Then someone is busy with the playlist management, handles which song or which track should be played next, which track was previous. So some logic is required for keeping the track of these tracks, who will be the first, who will be the next, and all that. Then when we are streaming the data, then the data is coming at some speed, and to make sure that the whole process runs smoothly, then before beginning to play the song, sufficient amount of data is first fetched and then dumped onto the buffer. And once sufficient data is available on the buffer, then only the song or the music starts playing. And as the music is playing in the background, the new data is getting from the stream and dumping onto the buffer. So make sure that the data full of buffer size is always available, so that the music player will not starve out of data. If at all the data is not available, then the music player will stop and keep waiting for the data to be streamed onto the buffer. And another thread is busy in synchronizing the library, that is scans the folders, update the playlist in the background. So we may be creating a playlist, some song is running and we are creating some playlist, or some playlist is currently active, but in the background we are creating some other playlist. All such things are happening in parallel. Each activity is taken care by one thread. This whole thing in fact is one process for the user. It's just a music player, but music player is performing so many activities then we cannot have a different process for each activity. So what we can do is we can have a small component of each process and call it a thread. So there are multiple threads, and each thread knows what to do, when to do, how to do, and all that. So they are all the threads. When they work in sync, then the whole process will work in the proper way. So that's about what a thread is. So the process here in this example is the music player, and the threads: one thread visible part, one thread audio part, one thread quality of the music, one thread getting the data from the backend, one thread talking about decoding, decompression, one thread talking about what user wants, which song to be sung, which song to be played, whether to play or pause or stop. All these activities are taken care in the backend, and the user is totally unaware of all this. The user is just allowed to just press one button, relax, and enjoy the music. All this is just possible because a process is working under multi-thread model. So that's about what a thread is. As an example, we can understand better. If you find this session of any use, so please do like, subscribe, share with your friends, and don't forget to comment. Thank you. In the operating systems topic. Now the next issue to look at is process scheduling. The process scheduling is necessary because the number of processes are quite more in number compared to the number of CPUs we have, and we know that one CPU can handle any time maximum one process only, and number of processes are quite more than the number of CPUs. Therefore some arrangement is required so that all the processes will get some share of the CPU, so that each process can execute its task. So in this, the process scheduling comes into picture. It is a method by which the operating system decides which process should get the CPU next, and how long the CPU should be provided to the next process. This has to be done considering some issues like the scheduling should ensure that the CPU usage is maximized. Each process should have a minimum waiting time, minimum turnaround time. So in all, the waiting time, turnaround time of each process should be minimized. So make sure that the scheduling is done in such a way that the process faces minimum waiting time and minimum turnaround time. What these mean, we just look in. So when the process wants to execute, it comes into picture, and from then how long it takes to get the attention of the CPU is what we call the waiting time. At the time the process came to existence, and how long it took to complete the action is called the turnaround time. That means we want a process to be attended at the earliest, that makes minimum waiting time, and once the process is given chance, then we should ensure that no other process come in between, so that the total time required to complete the task also minimum. But yes, we do have different situations where other process do come in between. So we need to minimize the waiting time and the turnaround time. That's what a best scheduling system should be. And also we must ensure that each process gets a fair chance to execute itself. Not that a few get chance and few keep waiting indefinitely, and all that should never happen. Make sure that a fair chance is given to all the processes. And it should provide responsiveness for the interactive systems. When it's interactive system, then we must ensure that our CPU is ready to interact whenever we do get input from the external world, or when we are working on interactive systems, then the external world may be slow In that case, instead of making a system wait for the event to occur, we can ask some other process to continue. So that way the usage of the CPU can be improved, and the waiting and turnaround time need to be minimized. So we need to ensure processes get a fair chance, and during interactive systems provide proper responses and all that. Now, how this whole thing happens? So for that we do have what we call queues. There are many types of situations, many states we have seen in the previous session somewhere about the process states. So when the process is ready to run, when the process is ready to execute, or when a new process comes into existence, that means it is loaded from the secondary drive to the main memory, the code is loaded and all the PCB is created for that, and that becomes a process. And once the process is created, it becomes a ready process. So once the process is ready to run, then it is dumped onto the ready queue. So in this case, two processes are waiting to be run. So process 7 and process 2 are waiting. So process 7 is given chance earlier, process 2 will get chance later. That's what this is saying. So from the once we want to allocate a new process, then process 7 gets the chance. After process 7, process 2 will get the chance. Then we have another queue which talks about any process is waiting for data to be read from the magnetic tape. So currently nothing. So there are two magnetic tape unit queues are there. For magnetic tape 0, nothing is waiting. Magnetic tape 1, nothing is waiting. Yeah, there is disk system in our computing system. Then there is one disk, that is disk unit 0, and 3 processes are waiting for the disk to be read. So process 3 is in the beginning, then 14, then 6. So if process wants to read from the disk, so it gets to the disk queue, and currently process 3 is waiting for its turn, and whenever the disk reading system is free, then process 3 will get the chance to read the disk. Once that is done, then process 14 gets its chance, and after 14 process 6 will get its chance, and so on. Same way, terminal, maybe some process may be waiting for some key to be pressed. In this case, process 5 is waiting for some key to be pressed. So these are the various queues we have. So there are two processes which are in ready state. That means anytime a CPU is available, they are used to run the process. So from the ready state, they can be switched to the running state. And then there are 3 processes waiting for data to be read or written to or from the disk, and 1 is waiting for the terminal. So that's various queues we have in this example. Then what exactly happens? So we said that there are queues and all that. What exactly happens? So that can be explained through the queuing diagram. So there is one queue which we call ready queue. So whenever a new process is created, it gets onto the ready queue, and the process which is in the front will get a chance to use the CPU. So the front in the queue will start using the CPU, and if the process completes its activity, then it gets terminated, or it may be stopped. The process may be stopped for many reasons. One reason may be the process wants to use some IO device. IO device definitely is very slow compared to our processor speed, and we don't want our processor to unnecessarily wait indefinitely for some IO action to take place. Therefore we just stop running that, and the time allotted to that process is stopped, and that process is put onto the IO queue. So there may be many processes wanted to use IO, so all these processes are put under IO queue. So the queue means first come first serve. Whoever asked the IO first will get chance to use the IO first, and second one will use second, and so on. So that may be the reason. So once the process wanted to use some IO, then that process is no longer in the running state. It get back onto the waiting state, and this is waiting for some IO to happen, and it is put under IO queue. And when that IO action is done, then that process comes back onto the ready queue. That's one reason. Another reason, because we may be working on time shared way, then each process is given some fixed time, so preemptive type of scheduling. Then a process is allotted the CPU, so the process from the ready state goes into the running state, and it will be in that running state for one quantum of period. And once that period is over, then it has to move out and come back to the ready queue, and the next one in the queue will get a chance to run. Or the process which is currently running may ask for a fork operation. So when a fork operation is done, then a child is created, and then a child is allowed to execute. And till the child is running, the parent process has to wait. So it will be in the waiting state, and the child process continues to run. And once the child process execution is completed, this parent process is put back onto the ready state. Or the process may be stopped for some IO operation, like want to read data from the keyboard. Want to read the data from the keyboard, then you can imagine the response time of the human. So very slow, and we talk in terms of the keyboard usage rate. We talk in terms of pressing keys per minute, so 60 keys per minute or 40 keys per minute and all that. So we talk in terms of per minute, and we are working with a CPU which works in nanoseconds, and the pressing of the key takes seconds, sometimes minutes, and we don't want our CPU to waste time waiting for that. So instead it is just put under the waiting state, and waits till that interrupt occurs. Interrupt occurs means we are waiting for keyboard, some key to be pressed. So when a key is pressed, it interrupts the processor. So interrupt occurs, and when that interrupt occurs, the corresponding actions with that interrupt are taken, and then the process gets back to the ready queue. So this cycle continues. Maybe for IO request, the running state goes into waiting state, or maybe because of the time allotted is done, then get back to the ready state. Or a child is created for operation, then wait for the child to complete, and then get back to ready state. Or waiting for some interrupt to occur, then wait for that. When that occurs, get back to the ready state. So that's what happens when we work with schedules. So talking about a scheduler, there are basically three types of scheduler. One is the long-term scheduler, which we call job scheduler. That means it is somewhere related with creating a job or creating a process. So a new process is created. So creating a new process means the code from the secondary drive is copied onto the primary memory, and this happens only once. And once the process completes its job, then it gets terminated. So this happens only once created and once terminated, and all other time. So for every process it happens once, and it is quite slow, very less frequently it is done. Then comes a medium term scheduling, where we make the jobs to wait for some event to happen. So here we have shifted our state from running to wait for some IO request, and this IO request takes some longer time, but definitely not as long as this time it is created and destroyed. It is a very slow process, whereas in one run many times IO activity may be taken, so it's a medium term. and then we have short term, which we call CPU scheduler. So the process which is ready is scheduled and becomes running, and when the time quantum is completed, it is put back onto the ready state, or when other process of having higher priority comes on the scene, then a process with lower priority will be put back onto the ready state, and then the high priority process will be made to run. So that's what happens. It is switching between the ready and running alternately, so it is quite frequently occurring. So that's something about process scheduling, all that. So if you find this any use, please do like, subscribe, and share with your friends. Have anything to say, please comment. That's it for now. Thank you. The next issue to look at is about context switching. Context switching is the process where the CPU stops executing one process and starts executing another. So it is the process where the CPU stops executing one process and then it starts another one. So one process which was running now will be stopped and made another process which was wait in the ready state to run. So the process which was running will now be changed to either ready state or waiting state or termination state, or the one which was waiting will now become running. So that is what a context switching is. So when the context is switched, that means if it is not being terminated, when the process is not being terminated, and if it is stopped temporarily to allow some other process to continue its execution, then we should know where we had stopped this process, and when next time this process gets the chance to run, we should be able to start from the position where it had stopped and start executing from there. So for doing that, the operating system must save the state or the context of the current process, and then should restore the context of the next process, which if it had stopped somewhere earlier, and if it's supposed to start now, then that old environment has to be recreated and then it should start. So each process can resume exactly where it left off. Say it has A and B were the two processes working. A starts working. Sometime it is found that A should stop and B should come back, or B should start working. So A has done some part of it, and before giving control to B, A should save all its environment, and the control is given to B, and B will start running. And after some time, the time for B is out, then A should again come back, then B should save its environment and then give control to A, and this switching takes place, and this switching is what we call context switching. So before going out, our process environment has to be totally saved, so that next time when it comes back, the exact same environment has to be recreated before continuing the execution. Same way, when one process goes out and another process comes in, then it should recall the old environment when it was stopped earlier. What was the condition? The whole environment should be recreated before the next process is being started. So that is context switching. Context, the saving a snapshot of a process working environment. That's usually the process control block, is what talks all about the context. So context, if you just look at what all details a context will have. So he talks about the CPU registers, when a process stopped working, what was the last instruction it has executed, and what will be the next instruction that has to be executed. The next instruction to be executed in that process will be there in the process program counter. Then what are the stack contents and what was the top of the stack? The stack pointer has to be noted. Then general purpose registers, so many general purpose registers are there inside the processor. Contents of all these have to be noted down somewhere on the main memory, so that next time when we come back, that whole thing has to be copied and exactly as it was now. Program counter is the address of the next instruction to execute. Stack information that talk about the local variables, return addresses, function calls, all details will be there in the stack. Then process state, it just says when it was running, what state it was in running state. Now when you stop it, what happens to that? Will it go back to ready state, or is it stopped because of some big event to take place, wait for a very long time, then it should go to waiting state or block state and all that. And then memory mapping, so this process which is stored onto the main memory may be scattered in different positions, which we call tables or pages. So it just tells which pages occupy our process and all that. So this details about paging and all that will come the next session when we deal with the memory management. Then security informations like the privilege levels, user credentials, etc. All these bundled up. This whole thing talks about the environment of our process, and this whole thing is what we call a context. So why do we require context switching in the first place? So that is to support multitasking. That means multiple processes are sharing one CPU. So that makes things easier for many reasons. Number one, the response time of the user, that means a human, is in terms of seconds, milliseconds, and the response time of the system is in nanoseconds. Then if a process is stopped for few microseconds and attention is given to some other process, and after few microseconds our process again comes back to life, we can't notice that our process was stopped for few microseconds because our response time is in milliseconds and seconds. Therefore it is not possible for the user to know that the process was stopped for few microseconds or some nanoseconds. So that is quite impossible to know. So this whatever inability can be taken as a boon, and we can make many processes to run one after other in a cyclic way, so that anytime the CPU is allotted to one process, and for a short period the CPU is allotted to one process. So process A runs for some time, then B, then C, then D, and back A, B, C, D, A, B, C, D. So this way, if it is being run, then between two periods where A was running, it is so short period that we don't realize that A was not running for some time. So we feel that all A, B, C, D are running parallelly, as if for the slow user it appears as if A, B, C, D all four are running on four independent CPUs, but in reality only one CPU is there behind the scene, and this time sharing is done. And because this time sharing is done for such a small period, we won't be able to notice that it is changing. The process is waiting and running, waiting and running, waiting and running. With this switching we can't notice, and this property can be made to use, and we can support multitasking very easily, and that's where the context switching is required, because ABCD, ABCD, ABCD. So when A has was forced to stop executing and given chance to B, then A should know where it had stopped, and next time after A comes back, then where A had stopped earlier, the same place it should start. The whole environment has to be exactly the same. So that's where the context and the context switching comes into picture. So this another reason is when we want to switch between the user and kernel mode. So whatever user is working with, so it is working in the user mode, and if we want to get into the kernel mode, so some system calls and all that will run in the kernel mode. So when we are shifting from user mode to the kernel mode, we should remember what was the situation at that time of the user. Then when the kernel mode action is done, it will return back to the user mode, and while returning back it should recreate the whole environment again, so that we don't notice anything is lost. So we don't want to lose any information about the user mode when it goes into the kernel mode and all that. At the time of interrupt handling, yes, so we do use the interrupts. So whenever some interrupt, like a keyboard reading the data from the keyboard, it is quite slow process, and we don't want our CPU to waste time on that, so we allot CPU to some other process, and the process which is waiting for the keyboard will go into the waiting state, and it will wait for the keyboard, some key to be pressed. So how does the process know that key is pressed? So whenever a key is pressed, the control circuit of the keyboard will send a interrupt information to the processor saying that key is pressed. So if you are waiting for this key, then you have input for you, so please read it. So when a key is pressed, the one which was waiting has to be shifted to the ready state. So for that, some other process has to run, and while doing that, so context has to switch. So same way, multi-threaded systems. So when you are switching from one thread to another thread, then the whole environment of each thread has to be saved, and that's where context switching is essential. Now let us discuss about two main operations that are performed on processes by the process management system, and they are creation of the process and termination of the process. A process usually is created by calling a system call fork. So let's just try to look at what would happen when we turn on our system. So when we turn on our system, the first process begins to work, and that is what we call the booting operation, and BIOS, which is stored permanently on the motherboard, will start running, and that starts booting the kernel. So the first part of the kernel that gets booted is a scheduling component, and let's say its PID is 0. Then we create another process called init that's going to initialize the resources. So what all resources are connected to the system, it just verifies that, and appropriate drivers are loaded, and these drivers are then activated. Because an operating system works for a common system which can have almost infinite components in it, can be connected with infinite components. So instead of working with everything and loading whole thing onto the memory, what is done is just look at what the peripherals, what the resources are connected to the system that are required for current running. Like keyboard is connected, mouse is connected, screen is there, and all that. So to make sure that these work properly, proper drivers are required, and looking at what keyboard is connected, appropriate driver is loaded onto the main memory. What the mouse is connected, appropriate driver is loaded onto the main memory under the kernel, and so on. So that's all happens during the init. And another requirement is to make the memory work as per our requirement. So we need to initiate the memory management component of that. So there is another process which is created through fork, and that is called page out, and this is taking care of the memory, its pages, and then updating the data on the pages with the disk and all that. So that is taken care by another process. Then say fs flush is the one which is responsible for the kernel operations related with file operations and all that. So that way we begin with the initial part of the one process, that is the scheduler, and then it creates another process in it. The scheduler creates one more process, page out. The scheduler creates one more process, fs flush, that's required for beginning the actions, and then init will initialize the internet component of that, and then initialize the display component of that, and this continues. So that's where the process creation is required, and that's how it is done. That is done through fork system call. So let's look in detail what fork does. Fork is a system call that is called in one program, and the program in which it is called the parent process. The process in which the fork instruction is executed is called the parent process, and once the fork instruction is executed, the whole copy of that is created on the memory separately, and then the two processes start executing. One process is the parent process and another process is the child process. And usually what happens is, when a new process is created, the child process, then the child process starts executing, and once the execution of the child process is done, then it exits, and the parent process is waiting till the child process exits, and once the child process exits, the parent process continues its other activities. So this is how it looks like. So just we look at one simple code. So here we have a PID variable that is going to store the process ID of the process, and now we are using system call fork to create a child process, and this child process once created will return an ID, and that is stored in the variable PID. So there are three possibilities. Possibility that child process may not be created, so something goes wrong, then it fails to create a child process. In that case, we get a negative number as a PID, so it returns a negative number for failure, and if the number is negative, then we get PID less than 0, then we just say that something went wrong, we display that error message and return a 1. And then it returns a 0 to the child process, returns 0 to the child process, and returns the ID of that new process created back to the parent process. So now through this, because the same thing is made 2 copies and both are running separately, now we want to make sure that one should work like a parent, other should work like a child, and here the PID value comes to our rescue. The same code is run 2 times separately, just a copy of that is run separately. One is called parent process, other is called child process, and same code has to be used, and they should do different actions. So to make sure that different actions are done, then PID comes to our aid. So the child process receives the PID as a 0, and if the PID is 0, that means you are looking in the child process. Then do something. So it is going to just go to this particular address and execute ls instruction, that is printing the directory onto the screen. Else. So one we have seen PID less than 0, that is getting a negative return value, that is when something goes wrong. If it is 0, that means it is a child process, and if it is neither negative nor 0, that means it is something greater than 0, which means that it is the PID of the child process which the parent gets back. Now it's not necessary for the child to know the process ID of the parent, but the parent has to know the process ID of the child it has created, because it has to wait till that child completes its action. So it should keep tracking whether that given child is stopped working or not. So for that, parent should know the ID of the child. A child need not know the ID of the parent who created it. This doesn't matter, but parent should know what all children it has created, and the parent should be alive till all the children are working. So once all child processes exit, only then the parent process should exit, otherwise it has to wait. So that's what we are talking of, but yes, I know it's a little confusing, so let's see the same thing in detail now. Yeah, we are here. This instruction we had just executed. So earlier this was only 1 copy, and after executing this instruction, this line 4 means this whole code we have another copy. This becomes parent process, and this is the child process. So in this process, this component will be run because it is getting a PID of the child. The PID of the child returned is 123. Therefore, it is neither negative nor 0. Therefore, this else will get into that. This PID less than 0, it goes in. If PID is equal to 0, it goes here. But none of them is true because what we have is PID of this child process, which is 123, and therefore it gets into the third component, which is the parent process. And here, parent process is just waiting for the child to complete its task. The other side, what is happening? We get a PID equal to 0 because this is the child process created, and in this case, where we have two sets of codes, two sets of variables. Here we have one variable PID, here also we have one variable PID. The value of PID in this set is 123. The value of PID in this case is 0 because it is the child process created by this instruction. Therefore, after this line, the PID here is 0. Therefore, it is not negative. So it moves here. It is 0. Therefore, it enters into this one and executes this one. And after executing this, once it is done, its work is over. And once its work is over, it returns 0. And when it returns a 0, then the process, which is a parent process, which was waiting for the child to complete, it gets a 0 back. And when it gets a 0 back, then this part is also, this word wait also is over. Wait means it is in the infinite loop till we get a 0 return from the child process. Once we get a 0 from the child, this part is over, and then it will return 0 to its parent. So whoever has created this will get a 0 back, and that if it was waiting for this to do, then it will continue its action. So that's example. I hope will clarify what fork statement is and all that. Now coming to termination. So when the process completes its execution and is removed from the system by the operating system. So when the process completed its job, then it should be removed from the system by the operating system. That's what the termination is. And after termination, all the resources are released, like the memory occupied should be released so that some other process can take that space. The files this process was using should be released so that other process can start using those files. Yeah, once a process is using a memory, then that memory should not be allowed by another process to occupy, because it's going to create havoc. And once a file is being used by one process, then we should ensure that the other process should not use the same file unless until it is essential. Then we must ensure that once a file is opened by one process, other process should not use it. So for that we have some mechanisms which we are going to look in the coming sessions. But once the work is done, we need to release these files so that other process who are waiting for that can now start using it. So that's what happens after terminating a process. And then we update the process table at any given time, which all processes are active. A big list is there which we call process table, how many processes are working, and details like name of the process, ID of the process, when it began, when and what resources it is using, which memory it is occupying, and who created it, and all details are there with that. And that process, has it created any child process? If so, what is the ID of that child process? All the details are there in this process table. So once a process is no more existing, then this process table has to be updated. That line has to be erased from the process table, otherwise it creates havoc. Then notify the parent process, if any, that the child process you have created is terminated. Now if you don't have any other work, if you are waiting only for termination of this particular process, then you can continue your own actions. You don't have to wait anymore. So for that, we notify to the parent process about the termination of this particular process. Then how many ways a process can be terminated? A normal termination, when the process completes all its job and it exits voluntarily. So it's supposed to do something and it has done everything, then it will close and say, I have done So let me get terminated, and it exits. So it calls exit or reaches end of the program. Like in C, we just written 0. That says that it's exit 1. So we just know that it has come to end of that program. So it just returns back 0 to whoever has called that and gets terminated. Maybe abnormal termination, forced to terminate due to error or unexpected situation. So you are trying to use some instructions that are not supposed to. That means divide by 0. You are trying to divide something by 0, then it's going to be into an infinite loop. So you want to make sure that you don't divide anything by 0. But what can we do? If you are trying to calculate A equal to B divided by C, and if for some reason C value was 0, and if C value is 0, and if you try to divide it, how do you divide? By successive subtraction. So B by C, if you want to do, we keep on subtracting C from B till the difference goes down to 0, and count how many times we subtracted. And if we try to divide B by C, and if C is equal to 0, then B minus 0 is B, B minus 0 is B, B minus 0 is B. To any number of times B minus 0, it's going to remain B only. It will never go down to 0, and hence this process will never stop. This is what we call infinite loop, and this is what we call the system has gone, what do you say? It's just a stop working. It doesn't respond to any keyboard, mouse, anything, nothing. So that's a crazy situation we get into if we try to run that. But yes, the next programming languages do have a technique to just check before any division operation is done. Just check what is C. If it is 0, just don't divide it all. Don't execute that instruction. But yes, without executing that instruction, the next instructions don't have any meaning. Therefore, what is fun in continuing? You just say it is not possible. So raise an alarm, say that here you are trying to divide by 0 and it is not going to get any answer, and hence terminate the process and display an error message saying that this is a problem, and hence it was forcibly terminated here. It did not complete its work. In between something went wrong, so we have stopped it. Operating system is free to stop any process if it is going to disturb the whole ecosystem. So instead of that, better stop it. So that's what we call abnormal termination. It is forced to terminate due to error or unexpected situation. This is due to runtime errors. This is not visible during compilation, it is only visible during running it. So all these are the runtime problems. So maybe divide by 0 or maybe invalid memory access. You are allocated a particular block of memory and you are supposed to use memory only in that, but if you try to access memory from neighboring process or something, then definitely alarm is raised, so it will be forcibly blocked. So why it happened? Maybe for many reasons, but yes, we are not allowed to access others information. One process should access information related with that process only. It cannot access other process information. If you try to get into other, then something alarm is raised by the operating system, and because of this problem, the operating system is allowed to forcibly stop the process. So that's abnormal termination. So it can be unhandled exception and all that. Then it can be killed by the operating system. So it is operating system is forcibly terminating a process. Like when the process is trying to use a memory, and for every process some memory is allocated, and if it's trying to use more memory than it is allocated, then the operating system should intervene and kill that process. Otherwise it starts indefinitely using the neighboring memory and may create problem to other processes. Or CPUs, when you are working with multi-processing environment, then each process is allotted some number of CPUs, then it should work within those number of CPUs. But if it tries to use more number of CPUs, then definitely it's going to create a problem, and hence alarm is raised and that particular process is killed by the operating system. So this is done to recover the deadlocks. What deadlock is? Yeah, we have this in detail to discuss when we are working with resource management, when we are working on process management, when more than one process is trying to use a resource like memory, file and all that. So we look at this in detail, what deadlock is and how to recover. So that one of the process is to kill a process that is holding some resources indefinitely, unwantedly, and creating problem to all other processes. So if one process is killed and all other processes can survive without difficulty, then it is better to kill one process, and that's what is done by the operating system. Or if you find that there is security threat in that process, so if the process is having some virus or worm, then make sure that the operating system kills it. So forcibly that particular process is ceased to exist. So this is forcibly done by the operating system, and that's what we call killed by the operating system. Or it may also be killed by the parent process itself. So parent process may explicitly terminate its child process. So here what happened is the parent process creates a child process through fork statement, and then it starts waiting for the child to complete, and some specific time is given for the child process to run, and if child could not complete its task within that period, then parent process may understand that so child process is having some sort of problem, and instead of creating problem to the whole ecosystem, the parent process itself can kill that child. So that's another option. So here the parent process may use instruction like kill or some similar. That's it for now. If you feel that this session is of any information, please do like, share, comment, and please subscribe to this channel. Thank you.
Hi friends, welcome back to another session on process management of operating systems. Now we want to see what inter-process communication is all about. It's one of the important topics in process management, the inter-process communication. So the processes, when we say do not share any resources, especially the memory, because we don't want one process to disturb other process. Therefore strictly the operating system will ensure that the boundaries of each process are properly defined, and the process will be allowed to work in that boundary only, will not be allowed to move out of that boundary, especially the memory. The modern operating systems use this process isolation. So why do we require process isolation? So there are three reasons for that. One is security. So this will prevent one process from accessing or corrupting another process data. So maybe knowingly, maybe unknowingly, maybe accidentally, or maybe wantedly, one process may try to overwrite the process on other process data, other process information, other process code. Anything can happen, and that's going to corrupt another process, and we don't want that to happen, and hence we will not allow one process to peep into another process. So they strictly are isolated. Another thing why the isolation requirement is there is the stability. Say one process crashes for some reason, then should not affect other processes, because each process has its own boundary, each process are having their own resources, and if that process crashes, then only that gets affected, and all others continue to work without any complaints, without any problem. So there will be stability in the system, so only the affected component gets switched off or whatever happens, but others continue to run. So for that reason we would like to keep the processes in isolation. Of course, memory protection. So each process has its own address space, therefore we don't want one process to leak into another process memory. So that's where isolation is required. It, in simple terms, means that one process cannot directly read or write into another process memory. That's as simple as that, that one process cannot read or write onto other process memory. So what does that mean? Even if two processes run the same program, their variables are separate. That means if two processes are created from same program, that means if the same program is run two times, then there are two different processes. Each process is run independently, and hence there won't be any connection between one another, so they are isolated and there won't be any common thing between them. So each thing like the memory, the program counter, the stack, the heap, everything is separate for each process, and therefore they don't share anything in common. So pictorially we can say this is one process, blue is one process, green is another process, and if the blue process tries to use some part of the green process, then it will not be allowed. That's how the operating system is created. But that's not all. That is, in general, one process should not interfere with other process, but there are situations where one process needs to communicate with another process. There we need some mechanism so that one process is allowed to communicate with another process, and that is what the interprocess communication is all about. So it is the mechanism by which multiple processes can exchange data or messages with each other. Yeah, this only through interprocess communication mechanism only communication between two processes can be allowed. As it is, they are isolated, and if you want any special thing to be allowed, like so once in a while if you want two processes to exchange data or some messages, then we should get the IPC in between and make sure that IPC takes care of this exchange properly. And because we are forcibly have to make IPC come into picture, then it is definitely IPC don't come in picture accidentally or by mistake or by noise or something. It has to be specifically called. Therefore, when we are specifically calling this component IPC to help us to share data or messages, then it's not happening accidentally. We very well know that we want to communicate with another process, and hence we are taking help of IPC. Therefore, by mistake, by accident, that cannot happen. So this ensures that the privacy is maintained as long as IPC does not come into picture, and only through IPC two processes can share the data, exchange the data, and so on. So the IPC is a component that allows to coordinate, cooperate, and share information even though they are isolated. Yes, they are isolated. Of course, the two processes are isolated, but only through IPC it is possible to share the information in a cooperative way, and IPC will coordinate how to communicate and all that. So it provides a mechanism to exchange the data or the information among the processes. That is possible only through IPC. Now, why IPC? Of course, that is for information sharing. So we do require sharing of the information among the processes. We require it, and when we require that, we need to use IPC. We can't just open this barrier and say that all processes can mingle with each other. Yes, we cannot do that. Therefore, we keep it isolated. Only now and then it may be required to have connection, then create connection for information sharing whenever required. Otherwise, they are isolated. So this will enhance the computation speed, because we can make subtasks to run in parallel, and they can communicate. These subtasks can communicate among each other and exchange the data. Then we can modulate, we can create the modules for every process and get into something like threads or sub processes, so that they can run parallelly and make the things easier for creation and writing, and then making the process faster, and it will be convenient as and when required. So how IPC enables sharing? So the IPC provides safe and controlled ways for processes to share the data, that is text, images, status updates, and all that will allow to communicate between the processes. And then signals or events, like one process is wanting to read the data from the secondary drive, and there is another process which is responsible for reading the secondary drive. So the first process will request the other process to read the data from that So then the second one will start reading it. When the reading is done, it will return back a message saying that reading is done and this is what I read and all that. So signals and events. So we just signal one process will signal to another process to say that please read this data from the secondary drive, and the secondary drive is read by another process. Once the reading is done, then the second process sends a signal back to the first process saying that the reading is done. So till now the first process can continue its own activity, because reading a secondary drive is quite slower, therefore it may take a longer period. So we don't want to waste our time of CPU, so the first process may continue working with some other activity. Or like sharing the file descriptors, we have pipes, message queues, shared memory, etc. are used for sharing this. So if you want to connect two processes for sharing, we can create pipes, or we can have message queues, or we can have shared memory. So there are quite number of ways to connect two processes for inter-process communication. So more details we see in the coming sessions. So as of now, that's it about the inter-process communication, why and how, what is inter-process communication, why it is required, and how it can be done. Basically two types of inter-process communications are there, which we are going to see in the coming session. So till then, signing off. So if you find this video of any use, please don't forget to like, share, comment, and please do subscribe to this channel. Thank you.
Hi friends, welcome back. Now let's look at the various types of inter-process communications possible. Mainly there are two types of inter-process communications. One is called the message passing. Since the two processes cannot directly communicate with each other because they cannot share anything in common, they are isolated, but each process can communicate with the kernel. Therefore, if process A wants to tell something to process B, then what we can do is process A can send a message to kernel stating that this message please forward it to process B. So process A forwards the message to kernel, the kernel in turn will pass the message to process B. So this way, through kernel, the message is being passed from process A to process B. So this is what we call message passing. But every time involving kernel is not that efficient in some cases. Therefore, we make sure that the kernel is not always involved for every pair of process want to communicate. Then what we can do is we can create a shared memory. Especially we create a memory and say that this has got a privilege such that both process A as well as process B can use this. Yes, there is separate memory allocated for process A, there is separate memory process B is allocated, but there is some memory which is allocated to both A and B in common. Now this common memory process A can use as well, process B also can use it. Now in this case, if process A wants to tell something to process B, then process A will write onto the shared memory, and then process B will read it from the shared memory. In this way, the kernel is not disturbed every time. So process A, process B, if they have their own common memory, then they can just use this common shared memory and share this memory for communicating. So that is the shared memory communication. Now let's see in detail what each one is. So let's begin with what is message passing. Message passing is a mechanism by which processes communicate and synchronize with each other by sending and receiving messages. So they do send messages and receive the messages, and by this the processes communicate among each other, and even they can synchronize. So when to use this? When the process do not share the memory. So message passing is used when we don't want to share the memory. We want to keep the two processes isolated, and we do use this special mechanism called message passing. Yes, of course, it is going to disturb the kernel each time one process wants to send a message to another process. It has to go via kernel. Yes, of course, kernel will be disturbed and kernel will be busy for assisting this message passing and all that. Then if we are creating the system in a modular way and still want to have proper secure communication, then we can go for message passing. Then if we are working across different systems, like different systems each having their own operating system, then we want to communicate between the process one working in one system, another process working in some other system, then we can't think of having a common memory, shared memory and all that. Then only one option is send message via the network. So use the network and send message from one end to other end. So one process from one system is sending some message to another process in another system, so that way we can work on. So that's how it all looks like. Process A sends message to the kernel, kernel in turn sends to process B. Here the kernel is always open for communication between every process. So each process is free to communicate with the kernel. Therefore it is quite simple to make the kernel as an intermediate point, so that the pair of processes can communicate across each other. Then there are two types of message passing. One we call synchronous message passing, wherein the sender sends the message and waits till the receiver gets the message. So it is tightly coupled communication. So in the synchronous message passing, what happens is sender waits until the receiver gets the message. So sender sends the message, the receiver should get it and then acknowledge that yes, I have got the message. Till then the sender will be waiting, and that's a tightly coupled communication. And in this case, both sender and receiver must be ready at the same time. It's not that sender sends sometime, receiver receives some other time. It's something like making a phone call. Both ends, both the parties must be available at the same time. Only one party who is calling is available and the other party doesn't pick it up, then the call is not complete. So the process is incomplete, message is not passed from one end to other end. It's like a phone call, so both parties should be available at the same time, and the sender will know that the receiver has received it and all that. On the other side, there is another type of message passing which we call asynchronous message passing, wherein sender just sends the message and continues execution without waiting for knowing whether the receiver has received it or not. It's a problem of the receiver. Just sender just sends the message and continues its own work. The message sent by the sender goes to the receiving end and then waits in the queue or the message queue or the mail box till the receiver picks it up. So between sender and the receiver there is a message queue or a mailbox where this message is dumped on, and the message will remain on this queue or the mailbox till the receiver receives it. It's similar to our email or WhatsApp messaging. We send our message, whether the other end is ready to receive it or not, it doesn't make any sense to us. It doesn't matter whether the other end is ready to receive or not, but what matters is when we want to send a message, we just send it. On the other end, it just will be waiting for the receiver to read it. Till it is read, it will remain in some place like a message queue or the mailbox, and when the receiver is ready to receive it, he'll just open the mail or open the message and reads it. So pictorially we can say the process A wants to communicate with process B. If it is a synchronous processing, then the process A calls for process B, sends a message to process B, and the process B will be working on that message, and then it will send back a response that he has received the message until process A gets a response from process B. Process A cannot continue its work, so it just waits for the response from process B. So here the process A was working, and once it wanted to call process B, then process B will continue working, and then process A gets back the response. Once process A gets the response back from B, then process A starts its work to continue. Whereas in asynchronous processing, the process A just sends message to process B. On the way, somewhere it is dumped on the message queue or the mailbox. So process A doesn't bother about what has happened. So for a short period of time, it just forwards the message, and after that, immediately the process A continues to do its work. And process B may be busy with doing something else, and then when it notices that it has received the message, then it will respond back. to process A that it has received the message or something. Like we get a green tick on the WhatsApp message, which indicates that we have our message is read by the receiver. So that's about the message passing. Message passing is mainly when for security reasons we don't want to have any common memory. In that case, we know that any process can interact with the kernel, therefore we make use of the kernel, so message is passed from one end to other end via kernel, and that is the logic of message passing. It's of two types, synchronous and asynchronous. Synchronous message passing is something like making a call, both ends should be ready, and asynchronous is like sending a message, SMS or WhatsApp message or email. It just goes and sits in their mailbox, and whenever the receiver is ready to receive it, just opens it and acknowledges. So that's about the message passing. Thank you. Hi friends, let's continue our discussion on inter-process communication. Last session we have seen some details about the inter-process communication, why it is required and all that, and then later we have seen how inter-process communication can be made through message passing. Now let us see how inter-process communication can take place through shared memory. Here the shared memory is an inter-process communication mechanism where multiple processes access a common memory region to exchange data. As we have seen in the beginning of operating system, we wanted to make sure that no two processes have something in common, neither they share the memory nor they share the resources, so they are isolated. We want them to be isolated, but in some cases we do require the information from one process to be transferred to another process, and that's where the information, the inter-process communication comes to picture. Here, instead of keeping them totally isolated, these processes, we can make a common memory region and say that all the processes can use this common memory, and one process can write onto this memory and another process can read from the memory. Because both the processes have access to that part of the memory, then through this we can make sure that the process communicate with each other. This is the fastest form of inter-process communication because it communicates by reading, writing directly to the shared RAM. So we don't have to send message to the kernel don't have to send message to the another process and all that. In doing this, what happens is there will be delay. The message from process A should first go to kernel, and kernel, if it is ready to accept the message, then okay, otherwise the message will be waiting in the list message queue, and once the kernel is free, it reads it and understands that this has to be forwarded to process B, then it sends to process B. So this all is possible only when this message reading, message forwarding has the highest priority at that time. Any other activity with the higher priority is with the kernel, then the kernel will delay this reading and forwarding message till the high priority activities are done, and definitely there will be chance of delay. But in this case, nothing like that. There is a common area where we can dump our information, and that common area is accessed by another process who can read it from there. So whenever process A is scheduled, it dumps its message onto the shared memory, and whenever process B is active, it reads from the shared memory. So there is no involvement of the kernel in between, there is no message queue, there is no waiting time and all that. Therefore it is the fastest one. Here one process, the first process, will create a shared memory segment, and other processes attach themselves to this segment. So first process, whatever wants to share the information with another process or processes, will create one shared memory segment, and other processes which want to communicate with the first one get attached themselves to this particular segment, and then they start writing and reading from this segment. So all these processes read or write to the shared memory to exchange the data. That's what happens. So it's very commonly used in the producer-consumer problem. So here producer produces the information and consumer consumes the information. And this very commonly used through shared memory, and we try to use a circular queue for sharing the information. The shared memory usually is used in the form of circular queue because the first message should be read first, second message should be read second, third message should be read third, and so on. Therefore, we require a queue, and we know that overall in a given time there is a maximum size of the memory requirement. We know that how many messages can be there on the store. So using that size, if we can make a circular queue, then things will be quite easier, and with a very limited number of limited size of memory, we could get most of the required things. So here this example is showing that the red one is used for writing and the green is pointing to the position where it is being read. So one process is trying to write and other process is trying to read, and this is continuously happening. So what happens? We know that this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are totally 12 slots available, and these 12 slots are sufficient for transmitting, because by the time the 12th slot is filled, the first, second, third, some slots will be read by the reader and they become free, and this can continue filling the next slots. So that way round it will be doing. So you can see that with only 12 slots the whole message is being transmitted irrespective of size of the message. Even the message size is bigger than 12, it is able to do that, and that's what we talk about in the producer consumer problem. Here what happens, we have a producer and we have a consumer. Producer produces the information and puts it onto the buffer, and consumer reads from the buffer. So instead of having a linear buffer, we better use a circular buffer as discussed earlier, so that in a limited size of the buffer we can make unlimited usage. So what does it do? So we have one place where we read it, and there is another place we write it, and there is a queue. So the next time we want to read, we read from here. Next time we want to write, we write into this slot. So this blank slot available next is ready for writing the new input, and this the first filled in slot is the one which we can read next. So once this is read, this header moves here, and once a new data is written, this tail moves here. So this keeps moving, and when the header and tail are at the same place, which means that nothing is available, so we can't read anything. But if the head is here and tail has come to this end, then it means the head and tail are in the same place. It also means that the buffer is full, so we can't write anymore. So we need to wait till something is read and a slot is made free. And when these two are in the same place, which means that whole thing may not be, it may be totally free, so nothing to read. So let's check that. So this is the writing system, that is the producer, and this keeps on doing forever. If the tail plus 1, and we take the modulo of the buffer size, if this plus 1, so if we are here plus 1 means this one, so if that is equal to the head, the out, then it means that we don't have any free space to write. So just keep waiting as long as in plus 1 mod buffer size is equal to out. Once something is read, then the out gets shifted, and this plus 1 is no more equal to out, and hence one slot is free, at least one slot is free, and in that slot we can write the next one after writing. So make sure to increment the tail end, that is what we call in this code, and in the figure we call it head for out and tail for in. So this is the producer system and consumer system. So this also continues to do. If in is equal to out, that means without both of them are showing same thing, then there is nothing to read. The whole buffer is empty, so there is nothing to read. And if they are not equal, that means the in has shifted to the next location, out is still in the first location. So we have written at least one data onto the buffer. That means the in has shifted to the next location, out is still in the same location, they are not same. That means at least one data is available to read. So wherever the out is showing, that is wherever the head is showing, that data to take it into the next consumed variable, and then make sure to shift the head pointer to the next location. And this we want to make it a round and round and round. Therefore all these increments are in the mod version. Therefore after if this whole thing has got n slots, then after n it should come back to the first slot. So if it is going to start from 0, 0, 1, 2, 3, 4, 5, 6, so this will be n minus 1. After n minus 1, automatically it should become 0. So if in is n minus 1, so n minus 1 plus 1 will be n, and n mod n will be 0. So it will come back to 0. So that way, so we make it a round, so that with only n slots in the buffer, we can keep writing and reading any amount of data. Only thing to ensure is if the buffer is full, stop writing. If buffer is empty, stop writing. That's only two things we do. So if the buffer is full, do nothing, stop writing. If buffer is empty, do nothing, stop reading. So this is the example where we are using two processes, one process that is producing the data and another process which is consuming the data, are working in sync through the shared memory. So that's about the interprocess communication. We have seen the requirement of interprocess communication, why it is required, what it is, and how it can be implemented. There are two ways of implementation. One is through message passing, and again in message passing there are two ways. One is a synchronous way, other is asynchronous way, and the second one is the shared memory. So that's it for now in the interprocess communication. Hope you enjoyed this journey. So if so, please do like, share, and do comment your opinions, what you want more, your feelings, and please don't forget to subscribe to this channel, share with your friends, and that's it for now. Thank you. Hi friends, welcome back to another session on operating systems. We are into the second module where we are looking at process management. In this, now let us see what a thread is and what a multi-threaded system is, and see how the whole thing works. So let's deep dive into this multi-threaded system. So before looking into multi-threaded, let us see what a thread is. A thread is basically the smallest unit of execution within a process. That means there is one process, and that process, if it contains some part of the process that can be executed separately without depending on one another, then each of these sub-components can be separated and each one can be called a thread, and these threads can be made to run concurrently. So that's what we say a thread is. Here, a process is an independent program where each one will have its own memory space, but a thread is a lightweight sub-part of that process, which means it will not have its own memory space. It will share the memory space of the process itself. So each thread under a process will not have a separate memory space for that, but it will share the memory space of the process. Now, multiple threads in a process share the same memory as just discussed, and each one has its own register, stack, and program counter. Because each one is running independently, each thread is running independently. Therefore, at any given instant, what are the values that are stored in the registers, we need to have a separate copy of that in the memory. So we need register contents to be stored in the memory. We need a separate stack for each one because each part of the code may be using stack. So we don't want to disturb one thread with another thread. So we have a separate stack for that, and we want to know what was the last instruction executed by a particular thread and what will be the next instruction to be executed if that thread is allowed to have a CPU. So the next instruction to be executed is stored in the program counter. So each thread is working differently, independently, concurrently, whatever we say. Therefore each thread is at different position and we need to keep track of them. So each thread should have a separate program counter, each thread should have a separate stack, each thread should have a place to store their register values in the memory. But the code for the process is common to all the threads. So the code of the process is one copy and each thread is using the same copy, so that we don't have to have multiple copies of the thread. We save the space. Then the global data variables and all that will be one copy, so there won't be any confusion. Each thread is not going to have their own different values, so but there has to be some way to synchronize and all that. So we have some other issues when these are being used by the different threads simultaneously. Then something we need to take care about synchronization and all that. So we'll look into that in detail in the coming sessions when we talk with memory management and all that. Then the program counter. So we look at this diagram, it's a bit clearer. So the whole circle is one process, and in that we looked at it's having two threads, thread 1 and thread 2. And because we are working with a single CPU system, then any given time one thread can execute. So only one thread will get a chance to work with the CPU. Therefore when thread 1 is working, thread 2 is not working. When thread 2 is working, thread 1 is not working. It's very clearly shown in the vertical timeline. You can see that when thread 1 is working, thread 2 is not working. When thread 2 is working, thread 1 is not working. And when thread 1 is working, thread 2 is not working, and so on. So this example talks about two threads. It can be same with any number of threads, but yes, any given time one thread is active because there is only one CPU which can execute the threads. Now looking at the difference between the single thread and multi-thread, whatever just explained was in words, so it can just disappear from the mind, but a picture is worth 1,000 words. So let me just show a picture to clearly differentiate between a single thread system and a multi-thread system. A single thread system is one where we have one other memory will contain the code, will contain the data, will contain the files that are open and all that. Then will contain the place to store the contents of the register. We'll have a memory reserved for the stack, and the thread will be executing. So this vertical line is talking about the time the thread is working. In case of multi-thread system, yes, we can see that multiple threads are working concurrently, but if you look carefully, the upper three blocks, the code, data, file, are common to all the threads. Register, each one has got a separate register place to store the contents of the register. Each one will have a separate place for their stack. The same way, each one will have a place to write the contents of the program counter, so that we know at what step each thread is running at any given time. So they will have the code, data, file, register, stack all are one set in the single thread system, whereas in multi-thread system there is only one set of code, data and files, only one set, but the registers, stacks, program counter are multiple numbers for one for each thread. So that's what a multi-thread system looks like. Now looking at one more confusion, that is single thread single processor, multi-thread single processor, and what about multi-processing. So that's just the same thing we have seen in the previous single thread single processor. Here we have everything one copy, whereas when we have a single processor multiple thread, then code, data and files are of one set, whereas each thread will have its own register, stack, contents to be stored in the memory. But in case of multi-processing, then which each one is one process. So each process will have its own memory space, which is going to accommodate code, data, files, register, stack, and all that. So this is one process, this is another process, and in this case it is a single thread. Each process is working with single thread. It can be this also. Each process can have multiple threads also. So in all, so today's operating system is quite complex. So it's a multi CPU, multi core, multi processing, and multi-threaded system. So we can imagine how deeply it is built, and how much complicated today's operating systems are performing, and that's it. So as of now, that's what we have in stock. So keep watching. If you find this of any use, please don't forget to like, comment, and subscribe, share with your friends. That's it for now. Thank you. Hi friends, welcome back. Now, after looking briefly about a multi-threaded system, let's see why threads are required, why they are essential for today's computing system. So threads are required to perform multitask concurrently within the same application, so that can improve the performance if we are working on a multi-core CPU. So if we are working in a multi-core CPU and one process can be broken into multiple tasks, multiple threads, each thread taking care of one task, and if each of these threads are attached to one core of the CPU, then we can see that all threads run concurrently. So instead of running this whole process as a one unit, if we can run independent components of a process as a thread, then we can run concurrently, each thread working with one core of a CPU, and this way we can speed up the execution and make use of proper usage of the CPUs. Then it is useful to keep the UI responsive. That means one thread may be working with input devices, one thread may be working with output devices. So we can concurrently make sure that all the IO devices, user interfaces, and all that are working almost simultaneously, so that will reduce the response time. So it becomes as if the whole thing is working in real time. So we can make sure that real time activities can be implemented through multi-threads. It's also useful to simplify the structure of asynchronous or parallel code. So when we are working with parallel code, then threads are very much useful to ensure that all these parallel codes can be taken care by the different threads. So it works faster and parallelly they can be run. So let's take an example of a multi-threaded server. So what actually happens with the server? Server is a process responsible for serving the client. So the whole process is the client wants something from the server, because when you talk about processing, when you talk about the information, instead of having made available at every point in the system, we can keep the central repository. So we can have one big computing system, so that all the major computation can be taken place there, or we can have a big repository so that all the information is stored securely there, and others just can put a query and get the answer. So instead of having their own computational capabilities, what we can do is we can keep one strong system with a central one, which we call a server, which serves for all the clients. So a client is a lightweight machine, so it doesn't have much resources. So it can place a query with the server, and the server will work for that client and return the solution. Now the issue is how this in real time should happen, because when we say a server, so the server must attend to many clients simultaneously. So if server is one process, and if one client requests for something, and if the server becomes busy solving that, then that server will not be available for other clients to respond. So what we can do now is we can make use of threads. So when a client appears for with some query, then server creates one thread of itself and says this thread takes care of the client. Now what is happening here is the central code of the server is one copy, the data is one copy, files one set, everything one set. So the thread which was created to take care of the client is created and that is attached to the client, and now the server is again ready to receive another request. So here you can see that the client will send the request first, then the server will create a new thread to serve this particular request, and now this thread is attached with the client, and once the thread is attached to the client, then thread will take care about what the client wants, so it will start solving it. So to solve that, it needs a code, the code is at the central level, then it needs data, data is at the central level, it needs files, it is there at the central level. The only thing is it should have its own registers, it should have its own stack, it should have its own program counter and all that, so that it keeps track of what it is doing. And the server now is starts waiting for another client to request. Now client 1 sent a request asking for something. So what happens, say if you are talking about some data to be retrieved from the central database, okay, the client says I want this data. Then the server, instead of searching for the data, it creates its own copy as a thread and says you look for what data the client is looking and serve the client, and the server will start waiting for another client to come up. When another client comes up, then another thread is created and that thread is attached to the client. So that way the server, the main first thread of the server is only worried about looking for client's request, and anytime a client request arises, a copy of that is created and that copy attached to the client, and the main server again continues to wait for the next request. So that's what keeps on happening. Or the same client may keep on sending different requests. So for one request, one thread is created, for the next request another thread is created, one more request, one more thread is created. Like we want information from one organization, then we send one request, then this thread is created and it is looking for the information, gathering all the information and combining that and all that and creating one better usable format, and then it sends back to the client. When this thread is busy doing its work, the client may ask one more request and ask for some other information. With that other information, the server says it creates one more thread and says the new thread to take care of the next request. So this way, not necessary that there should be multiple clients, the same client may keep on sending different requests. So for every request, one thread is created and that thread keeps track of what is requested and it serves that. And meantime, the main server process is working, waiting for the request from the client, keeps listening to the request. Anytime a new client sends a request, any new request comes up, a new thread is created and that thread is attached to the request. So that's one easy example. We can look at what a multi-threaded system can be of use, especially when it is a server process. Then without a multi-thread, it's quite difficult to get the maximum out of the resources we have, maximum efficiency at a faster rate. So high throughput, less response time and all that. So all these things depend on the multi-thread activity taken care by any process. So that's it for now. Thank you. Hi friends, welcome back. Now let us see the benefits of working with a multi-threading system. The first benefit is we get a faster response. In GUI applications, background threads keep the UI responsive, that is user interface always will be responsive. For example, a file is being downloaded by one thread while another thread is responding to the clicks the user is doing. So user interface, another thread is keeping track of what the user is clicking and all that, and other side one more thread is busy downloading some file, and another file may be busy uploading some file, and so on. Then when we are working with a multi-core system, then the performance we expect to improve, because the threads can run in parallel now. Each thread can take one CPU core, and they can run in parallel as long as they don't depend on one another. So all the threads of a process which can work independently can get one CPU core and then work parallelly, so that the whole process can be done faster. That's one issue. Second thing is, you don't have to make the cores sit idle. If it is a single process, then the whole process, one core will be taking care, and all other cores just are idle. Now if we divide one process into multiple threads, and if those multiple threads, out of which if n independently running threads are there, and these n threads can be allotted to n core of the CPU, and each of these threads can be run in parallel, concurrently they can run, and that keeps all the cores busy, so no redundancy, no wastage, and the process will complete at the earliest, and hence another process can be taken up. So overall the performance is going to improve. So faster execution of the CPU burn tasks like image processing simulations will find a very impact when we work with the threads. So when we are working on tasks like image processing, then we do have to do many activities. So sometimes we want to filter them, sometimes we want to find the edges, and sometimes we want the image to be blurred, some other time different actions to be taken. So if these have to be done in parallel, then each of these actions can be allotted to a separate thread, and each thread can work on that image data which is available centrally, and then each thread can take up by one core, and all these operations can be concurrently done, so the process becomes faster. So we expect a faster execution. Then efficient resource sharing, definitely the threads share the process memory and resources, but not like processes. Different processes never share the resources, but threads share the resources. Therefore, if I want to run two processes from the same program, if I want two processes from the same program, then what happens? If I call them two processes, then the two copies of the code will be put on the main memory, and all two set of data, two set of files and all that will be maintained separately for each process. But instead of calling them two processes, if you call two threads, one thread working for one operation, another thread working for some other operation on the same program, then what we need is one set of memory for the code, data, files and all that, and each core needs a small extra memory to store contents of the registers, contents of the program counter, or the other things like that. So efficient memory usage we can think of if we work in terms of threads instead of processes. So that will reduce the overhead and simplify the data exchange between the tasks, because if we think of processes, then we need to have inter-process communication. Additional overhead is required because these two processes are independent of each other, and if any exchange of information is required, then we should implement inter-process communication faculty, as we discussed in our previous sessions. So that becomes an overhead now, because these threads are sharing the same code, sharing the same data, sharing the same files, that is the same memory. So it becomes quite easier and becomes faster also to exchange the data. And then switching the context is also faster, that is from one thread to another thread. If we are changing, what all changes are required? A small set of information has to be stored that is related with that particular thread only. and each thread independently has a very small amount of information to be saved while switching the context. But when it comes to process switching, context switching in terms of processes, then the whole information has to be saved onto the stack and then come back when it comes back, which should be popped out of the stack and all that. But here we have a separate stack for each one. So performing context switching in terms of threads is quite simpler, faster, and these threads are lightweight and therefore require very few operating system resources. Then we have better system resource utilization we can expect, because one thread is waiting for some IO operation, the other thread can run now. The process is allotted a CPU time, the process is scheduled to run, and in that process, if it was a single process, then the process gets into some IO operation, then it has to wait. So instead of setting the whole process to the waiting state, what we can do is that one small thread can be put onto the waiting state and other threads can continue working with. So if one thread is waiting for some event to happen, which is quite longer, because they usually make use of secondary drive, or mechanical movements are required, like if you're working for hard disk or CD drive or DVD, or you are waiting for input coming from internet and all, and if the network is slow, definitely it's going to take a quite long time, and that long time in terms of processor speed is almost infinitely long. Therefore we can make others to work instead of wasting our CPU's time, and because of this the CPU is always busy and hence increases the throughput. So at a overview, if you look at it, each process is going to get its share of time from the CPU, and in that time, if the process is has to wait for some event to occur, then the whole time allotted to that goes waste. Instead of that, if this activity of slow usage, if it is taken care by one thread, then only that thread will stop working, other threads can continue working, so all the time allotted to that process can be fully utilized, leaving that action which is requiring input from slow devices or something. So this makes the CPU always busy and increases the overall throughput. And this simplifies the program structure for certain tasks. So multi-threading can make programs cleaner by breaking large tasks into smaller tasks, manageable concurrent activities. So while writing the code itself, if we start thinking in terms of multi-threaded environment, then we can write the code such that it can be easily broken into smaller threads. So the programming also becomes simple. Now if you look at what is this concurrent execution is all about. So if we think of a single core system, single core, single thread, then if there are four tasks being performed, and if this is being performed on something like round robin then T1 is allotted sometime, then T2, then T3, then T4, then again T1, then T2, then T3, then T4. So this T1, T2, T3, T4, task 1, task 2, task 3, task 4. So they go in cycles, because each one should get a share. So each one should feel that their task is on run. So you can't just keep one task complete and then take second one. Instead of that, if we can make interleaved this way, then it feels that T1 runs for some time here, then T1 runs for some time here, then T1 runs for some time here, and the gap between two instances when T1 is running is so small compared to the human response time. The human doesn't understand that for 3 slots it was not working, so it is working only once in 4 slots. Yeah, that all going to make it simpler, and the user doesn't understand that there is only one CPU working in the back, and the user has allotted 4 tasks to do, and feels that all 4 tasks are being concurrently run, but in reality this is how it is run. Now instead of single thread, if we have 2 threads, or if we have 2 cores, then each core can be given a separate task. So core 1 takes task 1, core 2 takes task 2, then core 1 takes task 3, then task 4, 1, 2, 3, 4, 1, 2, 3, 4. Now you can see that the task 1 here, it was come on the 5th slot again, whereas here on the 3rd slot itself it has come. So this is the advantage of working with multiple threads. So these threads are working in a single core system. If it is working in multi-core system like 2 cores, then the whole system gets running faster, and that way execution will be completed faster. So this T1, T2, you can take them as task 1, or in our current context, we can say that the process is divided into 4 threads. If the process is divided into 4 threads, then first thread, second thread, third thread, fourth thread, and then back to first thread, second thread, and so on we can run if there is only a single core. But if there are 2 cores, then T1, T2 goes to 2 different cores, then T3, T4, and this continues. And if you assume that there are 4 cores, then T1 goes to core 1, T2 goes to core 2, T3 goes to core 3, and T4 goes to core 4. As long as T1, T2, T3, T4 are independent of each other, that means to run T2, if you want to run thread 2, you don't have to complete thread 1, because while running thread 2, T1 has not yet completed, because again T1 is coming, again T1 is coming. That means T1 has not completed its work, but before thread 2 started working, which means that thread 1, thread 2 don't depend on each other. Same way, thread 1, thread 2, thread 3, thread 4, if they don't depend on each other, then you don't have to work in serial, you can work in parallel. So all these serial parallel activities and all that we take care, we look at when we are looking in detail about this in future sessions. So that's it. More core, more threads can be accommodated to each core, and hence the overall functioning can be compressed and the whole process can be executed faster. So that's it about multi-threaded system. Hey friends, the next issue is to look at various challenges we come across when we are working with multi-core systems. The challenges are dividing the activities for the different cores, balancing the load with each core, splitting the data when they are dividing the work to different cores, the data that is being used for each part of the code to be split, and then look at the data dependency, and finally the problems associated with testing and debugging. So let's see one by one in detail. Dividing the activities. So while dividing the activities for different cores, we need to examine the applications to find the areas that are divided into separate and concurrent tasks. So we need to examine the application so that we can divide them into separate and concurrent tasks. So ensure that each one can run individually on a separate core without any problems. So that's the first problem, is the whole process has to be divided into multiple activities, and while doing it, make sure that the various activities don't depend on one another, so that we can run them concurrently using a multi-core system. Then we must ensure that these tasks perform equal work of equal value. So we should divide the work or the process into threads such that each one gets almost equal amount of work, and each one also has an equal value of its results. So it should not happen that some process is having the least value as far as the total work is concerned, but for that least value work we are giving a separate core for that. So such things should not happen. So we must make sure that each core's work has equal value at the end. Then the data accessed and manipulated by the task must be divided to run on the separate cores. So we should make sure that the data is properly split, so that the task having the need to access any data should be separate, so that there won't be any issues when subtask using data which is accessed by another subtask or so on. So that creates havoc and may create problems. So we should have ensure that while splitting the code into multiple parts, we should see that data is also properly split, and ensure that the various components of the process or various subtasks are do not depend on one another's data. That means if one process needs the data that is output of another task, then these two tasks should be executed one after other, so should have proper synchronization. So if we feel that the data dependency is there among the tasks, then these tasks must be serialized instead of parallelly working. So all these have to be clearly envisioned before creating these tasks. And because these tasks are running in parallel on multiple cores, the testing and debugging with such concurrent programs definitely is very difficult. So we should have a proper guidelines, proper debugging and testing setup, so that even under this concurrent execution, we should be able to identify the problems, bugs, and we should be able to test them concurrently. So these are some issues we do face while using the multi-core processors, and the operating system should be wise enough to take care of all these problems. So that's it for now. Thank you.
Hi friends, welcome back to another session on operating systems. Now we are into the second module, process management. In this we are currently looking at multi-threading systems. So in this, now let us see how many different models of a multi-threading system. So what is multi-threading and what models are? So the models define how user level threads are mapped to the kernel level threads. It means how many user level threads are there, how many kernel level threads are there, how they are mapped. That is the model of a multi-threading system. Here each kernel thread will be allocated to one core of the CPU. So how does it map? So there are n user level threads and they will be mapped to k kernel level threads. So this n and k are variables, and in all there can be 3 possibilities, and they are many user threads to one kernel thread, or many user threads to many kernel threads, or one user thread to one kernel thread. So that's many to one, many to many, and one to one models. Let's see what each one is all about. So begin with many to one. Here there are multiple user threads and they are mapped to one kernel thread, and this one kernel thread is allocated one core of the CPU, and the thread management is done in the user space using a thread library, because these multiple threads are there at the user level. Therefore all this thread management, which of the user thread is to be connected to the available kernel thread and all that, all this management is done at the user level only, and for that we make use of thread library. And because there is one kernel thread, and that one kernel thread is connected to one core of the CPU, then only one thread of the user can run at any given time, even if we have a multi-core CPU with us, because on the other side we have only one kernel thread, and that one kernel thread can occupy only one core of the CPU. Even if there are multi-core CPU is there with us, it is not possible to make more than one user thread to work at any given time because of only one kernel thread. And by mistake the one user thread is currently connected to the kernel thread, and that user thread is blocked maybe for some IO operations or some other thing. Then till that is completed, no user threads can be changed. So scheduling of the user threads cannot take place, because one user thread has gone into the kernel space and the kernel is working with that thread, and if it is blocked because of some IO operations or something, then
till that is completed, no other thread will get a chance to use that kernel thread, and hence all the threads will be blocked. So the positive side of many to one type of connection is fast thread creation and fast switching is possible, and because there is only one kernel is only one kernel thread is being used, so minimum overhead at the kernel level we have, but nothing comes free. So there is a negative side also, the other side of the coin. Cannot have parallel execution because only one kernel core is there, only one kernel thread is there, which can use only one core of the CPU, hence no chance of parallel computing. And if that thread fails, then all the threads get blocked. So that is the problem with many to one. The other option is many to many. That means we have many user threads and there are many kernel threads. So there are many user threads, they are mapped to many kernel threads, and the operating system can dynamically manage this mapping. Which user thread should be mapped to which of the kernel threads and all that is dynamically managed by the operating system, and this will allow better scalability and parallelism because there are multiple kernel threads are there, and each kernel thread can work with one core of the CPU, and because of that we can make sure that parallel execution of these threads can be taken up. And if these threads are independent, they don't depend on one another, whether it is about the data or any other thing, then they can be run in parallel, so a better scalability can be achieved. So the positive part of this is it is very flexible and is scalable, and we can expect a very efficient resource utilization. The negative part of it is too complex to implement because there are many this side, and then the operating system is running around to manage the connections between the user thread and the kernel thread and see which user thread needs next one and which kernel thread is available next time, and that too complicated scheduling is to be done. So one scheduling for the user, other scheduling for the kernel, and then mapping. It's too complex to implement, and because of this complexity, lot of overhead is created while managing these mappings. So that is the problem with many to many. Now coming to the other one, which is one to one, that means each user process will be mapped to one kernel process. Each user thread is mapped to one kernel thread, and there is a true concurrency on the multi-core system. So there is no scheduling is required either in the user space or in the kernel space because there is one user thread attached to one kernel thread, and each one is independently working, and hence true concurrency we can expect in this type of system. And this definitely allows parallel execution, and blocking is the isolation is guaranteed. That means if one of the threads gets blocked, then others just continue without getting affected, because each thread is having its own kernel, each kernel is having its own core. Therefore, if one thread gets blocked, others without any hindrance continue without any difficulty. So the positive side, high performance on multi-core CPUs, and better thread isolations are possible here because each thread is independently working with its own kernel thread, and each kernel thread has its own core, so it is independently working. Then the negative side of that is more overhead due to more kernel threads are there, and limited number of threads are possible because the systems has a limitation of how many kernel threads can be created and all that. So the summary says that parallelism possible with one-to-one, parallelism is possible with many-to-many, but it is not possible with many-to-one. Blocking impact is very high in many-to-one, but it is very low in one-to-one. Overhead is minimum in many-to-one, but high in one-to-one. So the examples for using this on the operating system, the early Java, old version of Java was using many-to-one. Linux and Windows are working on one-to-one, and Solaris and the 264 working on many-to-many. So that's all about the multi-threading model. So if you find this anything interesting, so please don't forget to like, share, comment, and please do subscribe to the channel. Thank you. Hi friends, welcome back. Now let's see what a thread library is all about. It's a collection of functions that provides an API to create and manage threads in the user space. In the user space, the user needs some support to create a thread, work with the thread, manage the threads, because the user may not be having appropriate knowledge to create all these things, so it needs some support. But same in the kernel space, the kernel side is created by experts, and hence we don't require any APIs too. So for the user we do require APIs. So these APIs provide the facilities to create and manage the threads in the user space. So the library helps in developing, for creating, managing, synchronizing the threads and controlling the schedule behavior of the threads. It's abstract away the operating system specific implementation details, so the user don't have to know all the details about the implementation. So the whole system is put under abstract, and only what is important for the user, only that is made visible to the user, so that user can work with minimum efforts, minimum knowledge, can do it. So some of the functions provided by the thread libraries. So to create a new thread we have a create function. To terminate the current thread we have an exit function. To make a thread wait to finish is a join function, and to voluntarily give up the CPU. So if a thread is already scheduled and it is working and is using a CPU, and we realize that currently thread cannot continue using the CPU for some reasons, then we can just voluntarily give up the CPU. Then we have a mutual exclusive lock, that's a lock a resource. That means when one process is trying to use resource, then we must ensure that other processes do not use it. So we should put a lock before using any resource, and that lock is mutual exclusive lock. So we can lock the resource before using it, and after the usage is done, so we can unlock and allow others to use that resource and so on. So these are the various functions available. Then we have something called pthread, which is the POSIX threads. It's a standard API for multithreading in C or C++, which is supported by most Unix and Linux systems. So this allows creating and managing the threads, allows synchronizing threads using mutex and conditional variables, and the various pthread functions. You can see that you can pthread create, pthread exit, pthread join, pthread mutex lock, pthread mutex unlock, and conditional wait and signal. So let's take it an example. So here what is it trying to do is we have creating a thread named hello thread, which simply prints a hello from the thread, and once the printing is done, it just returns back, nothing is returned. Then in the main program we are creating one ID for the thread. A thread ID is created, which we call TID, and then we create a thread with that ID, and name of the thread we call it hello thread, which is one function we have already defined. So this function is attached to this thread, and then we say join. Join means the parent thread should wait till this thread TID is running. So wait for the thread to finish, and once the thread finishes its action, then it just comes out, and the parent thread will print that thread is finished and then return 0. So in all, what is it doing is we created a thread like a child process. Its name is the hello thread, and that's written here, and then we wait for that thread to complete its action. So the moment it is created, it goes there and starts working, and as long as this is working, the parent process will keep waiting. So that's the join, and once this process is done, then it prints finish and come out. So let's just look at the running of this one. So here the same program we have. If I just run it, it says hello from the thread, and then the thread is finished. So we can run it again. So hello from the thread. So if the thread is created, hello thread, and in the hello thread it says hello from the thread. So we can say modify this. Hi friends, let's look at another example of multi-threading. Here we have code that has got two threads, and these two threads were created, and then the two threads use this function to print the numbers, and this print number keeps printing from 0 to 4, and this is used by each of these two threads. And when we run this, so first thing is we create two threads and we make both the threads join. That means the main thread which created these two threads will wait till both other threads do their execution, and once it is done, then this will also close it. So if we run this, then what we have is this code which makes two threads. So this we are making two threads, and if we run this, then it says thread 2 started working, because the operating system will give a chance for thread 2 to start. So thread 2 went into execution, then it started printing 0, 1, 2, 3, 4. After thread 2 completed, then thread 1 gets the chance, then it prints 0, 1, 2, 3, 4. If I run this again, then in this case thread 1 comes first, then 0, 1, 2, 3, 4 is printed, then thread 2 starts its work, 0, 1, 2, 3, 4. If I make it another time, then again it happens other way. Now instead of two threads, if I make it three threads, then the whole situation now will work for three threads. And if I run this, yeah, thread 1, then thread 2, then thread 3, and if I run this again, then thread 1, thread 2, thread 3 only, in the same order we are getting. Now here thread 2, 0, 1 printed, then timeout, then thread 3 gets a chance, 0, 1, 2, 3 printed. Before thread 3 could print 4, thread 2 came back and it printed the remaining 2, 3, 4, and then thread 1 was given chance, 0, 1, 2, 3, 4 was printed, and for thread 3 somewhere in between 4 was also printed. So this is how the scheduling between the threads takes place, and this example very clearly explains. So that's it for now. Thank you. Hi friends, welcome back to another session on multi-threading. Now let us see some issues related with threading, the process management. So the various issues to look at is about the fork and execute system calls, cancelling the thread, signals handling, thread pools, thread specific data, and scheduler activations. So let's see one by one. So when one thread calls a fork, then there are two possibilities. One is immediately after the fork is called, there is an execution exec system call, and this will replace the parent code from the child code. It will not allow the child to continue executing the parent code. It will have its own new code. But if there is fork and there is no EXEC followed, then only one thread continues to work. So when we call this in the multi-thread environment, if the fork is called and it is followed by EXEC system call, then all the threads are duplicated. If it is not followed by EXEC, then only one thread gets duplicated. Now what happens is when fork is followed by EXEC, that's a recommended way of working with the fork, and it's safe also. So after the fork, the child process immediately calls an execution system call to replace its entire memory image. So that means whatever parent's memory image was there, it will be totally replaced with a new image, and all the threads and resources are reset, so it avoids problems like deadlocks or inconsistent states and so on. So one thread calls a fork, then other threads, if they are allowed to continue, then they may hold some resources, and because of that holding resources, it won't be able to release them, then a deadlock or inconsistent state occurs. So we recommend to use EXEC system call immediately after the fork in the child process, so that a new memory image is created for the child. It is very safe in the multi-threaded environment and used in servers, shells, and multiprocessing frameworks. Say here, somewhere above we have initiated a fork statement, and if that is equal to 0, that means the PID is equal to 0, which means it is talking about the child process, and the moment it gets in, the instruction is executed to list the directory. So here the child does not continue with the original thread logic, it's a new code is used for that. But if the fork is used without execution, then it is very risky. The child process continues running the same code as the parent code, and only one thread survives. Now what happens when one thread calls the fork, then that thread gets a duplication, and because it is not continued with the EXEC, therefore no new environment is created, and only that one thread continues to exist, and all other threads just stop working. And if other thread had logged any of the resources using mutex, then that will remain in the log state, and there is no chance of unlocking that, because the thread which has logged one resource is no more existing, because another thread has called fork and it has created its own duplicate, and it is running that, and that duplicate never knows that other threads were also existing from the parent thread. Along with the parent thread, other threads also were existing, so that is the child process, child thread doesn't understand, doesn't know, and hence there is no chance of running them, and hence the resources that were logged by other threads will remain logged forever, and that definitely will lead to inconsistent or partially updated state, and may in future get into a big problem like deadlock. Yeah, these all issues we consider when we look into our next series, the next module, when we look at memory management. So this can lead to deadlocks, race conditions, or crashes. Anything can happen. So it is always recommended when a thread is forking itself into another child thread, better use a exec command immediately after the fork, so that the child will create a new environment and other threads continue to exist, and they get their chance to run as and when the scheduler allows. So this is a example. If the fork is equal to 0, that means we are not using exec command here, that means the same code is being run, so can create many problems in the multi-threaded environment. So 4 plus execute, the child replaces itself with a new program. It is safe. Use cases will be shells, web servers, multiprocessing, and all that. If you want to use fork only, then child will continue to run the current code itself. It's definitely not safe in multi-threading environment. It is used in experimental or legacy code and all. Looking in the other perspective, the fork only way of creating new thread and 4 plus exec way of creating new thread. So the code executed by the child is the one same as the parent was executing, whereas here the code is replaced with a new program. Use case for fork only, the multiprocessing with the same code and 4 plus exec running a different program. Memory space, it is copied from the parent, but in this case it is replaced entirely. Example will be the background workers in a server for the fork only, or 4 plus exec shell launching a new command. So that's an analogy. Imagine a team of workers building a house, that is the process. If you copy the house and replace all the workers with a new plan, that is exec, everything starts fresh, no problem. But if you copy the house and let only one worker continue, then other tools or incomplete tasks remain, causing chaos. That's what we are trying to say. That each worker was doing their own work, and if you keep only one worker continue to work and stop all other workers, then other activities get stopped and it remains incomplete and definitely creating a problem. Then there is another issue of thread cancellation. This is a method to terminate a thread before it has completed its task, and it is typically done by another thread in the same process. So one thread calls for cancelling another thread before the other thread completes its job, and this is used when that task is no longer is needed. So if we think that the task that the particular thread is doing is no more required, then instead of keeping it alive on the memory and all that, we can just kill it and cancel that, so memory will be made available for some other actions. Or maybe because of timeout, another process like a scheduler may call to terminate a process, or application is shutting down. So the main application is shutting down, and that application has created many threads, and when the main application, that is when the process itself is getting terminated or shutting down, then all threads also must terminate. So the threads get cancelled. So there is one thread which is responsible for cancelling all other threads at the time when that process is being terminated. We'll take care of shutting down all the threads one by one. So that's thread cancellation. And there are types of thread cancellations. One is asynchronous, that is the target thread is immediately terminated. The moment we say stop, it stops working, and this can lead to resource leaks or inconsistent state, because when we say stop, we are not sure that that particular thread is using some resources and all. It has locked some resources for its usage, and without releasing them, if you stop it, then it's going to create a problem, and definitely it is not recommended. So it is like cutting the power mid operation, so it just hangs there whatever had happened. There's another one which is called deferred cancellation. Here the target thread checks periodically whether it should cancel itself or not. So if somebody says to cancel, then whatever work it is doing, it will first complete that and then cancel itself. And this one is the safe and the recommended method of cancelling any thread. So it works only at the cancellation points like read or sleep or thread test case. So this is a default way of cancellation is the deferred cancellation, and it is always safe and recommended. So that's a example. So now going into another issue, that is the signal handling. A signal is an asynchronous notification sent to a process by to notify it of an event. A signal is an asynchronous notification sent to a process to notify that some event has occurred. Like if we press Ctrl C or some alarm timeout and all that, signal has to be sent to the process, and that is sent through signals. And these signals allow the operating system and other processes to interrupt or communicate with the running process. So when a signal arrives, the operating system will interrupt the current process or communicate with the running process. So how it is done? So first thing is a signal is generated, and then the operating system delivers the signal to the target process, and the process after receiving the signal may ignore it. If you can allow to ignore, then it may be ignored, or it may use some default action. Whenever that signal is generated, one default action is written, so every time signal is generated, that default action takes place, or some custom defined handling action is taken, so that is a custom signal handler is run whenever we get a signal. So various functions. There is a signal, that is to register a signal handler. Seek action is the most powerful. The POSIX complaint as a handler setup. Raise sends a signal to the current process. Kill sends a signal to another process, and alarm triggers seek alarm after a delay. So seek action is the most powerful handler setup. Raise sends a signal to the current process. Whichever process is running currently, signal is sent to that. Kill, wherein we say which process to be killed by sending a signal. So this signal goes to that another process whose PID is written here, and then we'll kill that process. So alarm in seconds, then the trigger is activated after that delay. So the various possibilities, the default here, the operating system has defined the action. Ignore just neglects the signal, or customer handler, you can call your own function. Then when it is multi-threaded, we have options. Deliver the signal to the thread to which the signal applies, deliver the signal to every thread in the process, or deliver the signal to certain threads in the process, or assign a specific thread to receive all signals for the process. So when we are working with multi-threaded environment and we get a then the process gets a signal, then what can we do? So that signal may come with a label that this signal is meant for this particular thread. In that case, it applies only to that particular thread. Otherwise, the signal may be applied to every thread. So some signals are like emergency siren should be applied to all the signals in the process, all the threads in the process, or to certain threads in the process we can apply, or make one thread to receive all the signals of the process. Here there is one signal coming in and there are multiple threads, and signal may come with a tag about which thread it is sent to. So first one says applies to only that particular thread. Second one says signal comes, all threads respond to it. Another signal comes, certain threads respond to it. Or instead of keeping all threads waiting for signals, we can make one thread just to wait for signal and then take appropriate actions in for all the other threads. So two-level signal delivery. The signals are sent to the process, so sent using kill or the rise. Then signal can be handled by any thread that has the signal unblocked, or signal sent to a specific thread. Here the signal is sent to the process, whereas here it is sent to a specific thread. So we are using a p thread kill. Here it was just kill, and only that specific thread receives and handles the signal. So the best practice for dedicating signal handling the thread. So block all signals in all the threads. Create one thread with signals unblocked. So keep only one thread that can receive all the signals, and use seek-wait or seek-wait info in that thread to wait for the signals. So this way what happens, all other threads can safely continue doing their tasks. They don't have to wait for signals. So this way we can ensure that the signals reach one thread and only one thread will be waiting for the signals, and once the thread gets the signal, then it will inform appropriate thread what to do and all that. Then we have something called thread pools, a collection of pre-created threads that are reused to perform multiple tasks instead of creating destroying threads every time a task comes in. So yes, that's another issue. So every time we have a task, one thread has to be created, and when that work is over, the thread has to be destroyed. Instead of creating killing the threads, we can keep some threads pre-created and reuse them as and when required. The advantage is it reduces the overhead of creation and destruction and prevents resource exhaustion, because we want to have limited number of threads. Then this limited number of threads we can pre-create and keep using them. Then this resource exhaustion can be eliminated. Then improves responsiveness and latency, supports task queuing and load control. Then we talk about something thread specific data that allows each thread to have its own private copy of a variable, even if all threads use the same key or identifier. Each thread can have its own private copy of a variable. And in multi-threading, global variables are shared by default, and thread specific data lets each thread store and retrieve its own value without interfering with others. We would like to ensure that each thread works independently without disturbing others. So there's something called global data which every thread can share, and that's what we talked in the beginning when we were talking about multi-thread system, that the data has one copy of data is available and all threads will use that. But here we add one more a small private data for each thread to store its own values. So it is useful while logging, it is useful while error handling, and used as a thread local buffers and re-entrancy. So whenever we want to repeat anything, then we would like to know where we had stopped and where to start and all that. Then we have finally scheduler activations, so a mechanism that coordinates between the user level thread library and the kernel level scheduler. So this allowing efficient and flexible thread management to many threading models, as we have seen in the previous session. So there are some threads at the user level and there are some threads at the kernel level in the many-to-many model, many-to-many multi-threading model we have. And there is a mechanism required for scheduling which user thread should use which kernel thread and all that, and to make sure that it is efficient and flexible, scheduler activations are required. And here the kernel provides a virtual processor to the user space, and when an event occurs, like a thread blocks, a new processor is added and the kernel notifies the user thread library via a scheduler activation. So whenever any event like a thread is blocked, then the kernel will notify the user thread library via this scheduler activation that something is wrong. So user thread which was allotted a kernel thread has stopped working. So it informs to the thread library that this particular user thread is no more working. So next time when you are trying to schedule it, make sure not to schedule that particular user thread and all that. All these things are done through the scheduler activation. So these are some issues related with multi-threaded systems. So that's it for now. Thank you. We are into the operating systems. In this we now are in second module where we are looking at process management. In that now we'll start looking at what process scheduling is all about. So let's just dive into the process scheduling. So the first question is about what scheduling is and why scheduling is so important in operating systems. In a multitasking world, multiple processes need to share the same CPU. Without a scheduler, the CPU would sit idle or processors would fight for resources, causing inefficiency. Scheduling ensures that the CPU is used optimally, with processes getting fair and timely access. It prevents one process from taking over while giving others the chance to run. It even plays a key role in real-time systems where timely execution is critical. So whether it's making sure your word processor keeps running while your music plays or ensuring life critical system work on time, scheduling is a efficient system operation. So scheduling is what all about. So here the scheduling is the process by which an operating system decides which process or thread to execute at any given time. The whole problem is we have limited resources, limited CPUs, and we have large number of processes or threads which do want to use the CPUs and resources. But anytime one CPU can work with one process or one thread at any given time. Therefore, some mechanism is required to ensure the smooth functioning of all this. That is where scheduling comes into action. It ensures a fair resource allocation so that all the competing processes or all the competing threads get a fair chance for using the resources. So proper resource allocation is taken care by the scheduling system. It maximizes the CPU utilization and it provides efficient user experience at the same time. How does it do? Let's check that. So usually when we are working with any thread or a process, it is an interleaving of two bursts, one CPU burst and one IO burst. So as long as the instructions available on the main memory are being executed, it will be the CPU burst because all are working at almost a CPU speed. So the session will be running efficiently. But the moment we want some data from the IO device, if we want to interact with any of the IO device, and naturally IO devices are very slow in their speed, like say hard drive or CD drive, they do have mechanical movements, and these movements are obviously quite slow compared to the processor speed, and hence it makes no sense in making the processor to wait for this IO operation to complete. So whenever IO operation is being performed, that's what we call IO burst. Whenever instructions from the main memory are being executed, then we call it CPU burst. So usually any process consists of alternate CPU IO bursts, and whenever CPU burst is going on, we don't have problem, but when IO burst is going on, yes, we do have problem. Instead of allotting or making the CPU wait for this IO action to complete, why not make this CPU available for some other process or the thread? That's what is the main mindset behind the CPU scheduling. So whenever we have an IO burst of one process, we can allow another process CPU burst to take up. So alternately or one after other. So whenever one process gets into IO burst, so it is wise enough to stop that process there. That means to take out the CPU from that process, let the IO module take care of loading from the IO and put that in a buffer and keep it ready for immediate transfer to the CPU whenever the IO task is complete. But as long as IO task is going on, our CPU can be allotted to some other process. So that's the basic problem we had when we were working on this IO burst. So the CPU scheduling is the basis of the multi-programmed operating system. So when we are working with multiple programs, then if one program or the one process stops for some IO burst, then another program can be allotted the CPU and the other process can continue its processing. So this allows other process to use the CPU when one waits for IO. So this type of activity is what we call short-term scheduler or CPU scheduler. Here we are scheduling the CPU to various processes depending on whichever process is available for execution, and if any process is not ready for execution, it is waiting for some other event to occur which is quite slow, then it is neglected currently, and that is what is the job of CPU scheduling. So when you look at the types of scheduling, then basically there are two types of scheduling. One is called preemptive scheduling and other one is called non-preemptive scheduling. In preemptive scheduling, we allot a particular time for any process to use the CPU, and once the time is over, then forcibly that process will be stopped and the CPU is allotted to some other process. So that's a preemptive. That means we don't have to wait till that process complete. Before completion of the process, we can stop the execution of that process and can be allotted to something else. So something like a emergency issue, priority process. So when a low priority process is being executed and midway some high priority process comes into picture, then we have to stop the low priority process and make sure that high priority process is taken up and all that. So those are the preemptive type of scheduling, whereas other way there are non-preemptive type of scheduling. That means if CPU is allotted to one process, then as long as that process is working, the process, the CPU will be at that particular process. So only when the process is complete, then the CPU can be allotted to some other process and so on. So that's preemptive, non-preemptive, and under preemptive we have many types of scheduling algorithms like priority scheduling. That's just what we just said. That the various processes have different priorities. So depending on the priority, scheduling is done. Whenever a high priority process comes up and a low priority process is being executed, then that low priority process is stopped or interrupted, and then high priority process is allowed to continue. It's just like a ambulance coming on the street. The moment ambulance comes on the street, highest priority is given to the ambulance and all other traffic is stopped and ambulance is allowed to travel, because that is a life-saving problem. So we have to make sure that it moves as early as possible. Then we have something like a shortest remaining job first, longest remaining job first, round robin. Yeah, there are many such algorithms under preemptive. Under non-preemptive, we have first come first serve. Yes, that's a very common thing. Whoever requested first will get the chance first, or whoever job is small will be getting chance first, shortest job first, or the longest job first, or the highest response ratio next, and all that. So these are some types of scheduling algorithms. So basically two types: preemptive, non-preemptive, and under them many are there, and we keep looking them one by one in coming sessions. So keep watching, and if you find the sessions of any interest, please ensure to like, comment, share, and please do subscribe to this channel. Thank you. Hi friends, welcome back to another session on operating systems. Now we are into the CPU scheduling, and let's see the various criteria on which the CPU scheduling can be accounted for. So they are CPU utilization, throughput, turnaround time, waiting time, response time, and so on. So let's see one by one what they mean and how they are influenced by the scheduling. So starting with the CPU utilization, it is how effectively the CPU is being used. So when CPU is available, so how much of the time the CPU is working and how much of the time CPU is idle, either having no work or waiting for some external event to occur, will decide the utilization of the CPU. So we want it to be as high as possible. We want to keep the CPU as busy as possible, and it is expressed as a percentile. Ideally, it is usually between 40 and 90% of time the CPU will be working. So the higher utilization, the better throughput and better resource usage we will have. And the measurement, the CPU utilization is a good metric when we are working with servers or real-time systems. So the servers, real-time systems, when we are working with them, the CPU utilization metric is a good measure of how efficiently our system is working and all that. Then comes throughput. It's a number of processes completed per unit time. So in a given multitasking, multi-programming environment, the number of processes being completed in any given unit time is what is defined as throughput. So it indicates the overall system productivity, and it all depends on how the processes are being scheduled, and throughput is one of the important metric to find out which scheduling technique is better for a given situation and all. And more the throughput, the better is the performance of the system. So it is a good measure when we are working with a batch processing systems. So when we are working with batch processing system, then this throughput is a best metric to measure the system performance. Then we have something called turnaround time. It's total time taken to execute a process. That means it's not just the execution time, it is the time when the process came to existence. That is, with a request, the process has come to existence, a program has become a process, and then the time it completes its work, that whole time is called the turnaround time. So we have something called arrival time. That is the time when somebody requests some process to begin the work, and for many reasons the process may not be given the CPU, therefore it will not be running, and hence it will be in the waiting state. And once the CPU is allotted to that process, then it starts running, which we call burst time, and finally it completes its job. So the turnaround time is the time at which the job is completed minus the time when it arrived. So that's the total time from the arrival since completion. The total time is what is called the turnaround time. It is measured with a formula, completion time minus arrival time. So this includes the waiting time and the execution time and the time taken for IO activity. Because this also, IO activity is also part of the process. Therefore, the turnaround time includes the waiting time. That means the time for which CPU is not allotted to the process. And when the CPU is allotted to the process, the time it takes to complete the task, that is the execution time. And in between, it may keep working with IO activities, and all the time it takes to complete those IO activities are all taken together. That makes the turnaround time, the time the process is waiting for its turn to get the CPU, and the process working under execution, and all the time it is waiting for some IO activities. And the lower the turnaround time, it is the better. So we would like to ensure that the turnaround time is as small as possible, and it's a good measure for short and user visible jobs. So the jobs which are short and the jobs which are very much visible to the users, that is foreground processes, it's a best tool to measure the performance. Usually if the process is running in background, it may not make much sense, but what makes sense to the user is what is there in the front end. So the user can appreciate if the response comes fast to the user. So it only matters when we are working for user visible jobs, but those jobs which are in the background, the turnaround time may not be that easily appreciated. And then comes the waiting time. It is the time a process spends in the ready queue. So we discussed earlier that there are various states of a process. So one of the states is the ready state. So how long a process is there in the ready state, that is what we call the waiting time. So the waiting time is also measured in terms of the turnaround time minus how much time it takes for a CPU burst, that is how much time CPU takes to run the program or the process, and how much time a process was waiting for some IO activity. So removing all that, that is, we are only worried about the process waiting in the ready queue, not waiting for the IO operation or not waiting for the process to get completed with execution. It's only the time the process is in the ready queue. So we want it to be as small as possible. So this is the pure time wasted without execution. Whereas in the CPU bus time, the actual code is being run, and in the IO time, some data is being transferred from main memory to the IO devices. So that's also part of the game. Therefore, we cannot assume the IO time as a wastage of time, but because it is slower, then we had given a separate name for that. CPU time is the one which is working at a higher rate compared to the IO. Therefore, we have separated the two actions, and we want to make sure that throughput is high. Then we don't want any CPU to wait for the IO event to happen for any given process. So when one process gets into IO burst, then the CPU may be alerted to some other. Therefore, we have separated these two timings. But in all, the CPU burst time is also working for the cause. IO time is also working for the cause. So we cannot claim that the CPU is being wasted in any of these two times. So it is the pure time that is being wasted without execution. So that's the total time it takes from the initiation to the end is the turnaround time. In that, how much time we have used for running the code is the CPU bus time, and in that time, how much time we have been waiting for the IO activity to complete, that is IO time. So leaving the CPU bus time and IO time, what is left in the total turnaround time is what our process has wasted. So that is the waiting time. And the scheduling, we aim to minimize this waiting time. So we would always want to ensure that the waiting time for any process is ideally 0, but practically as small as possible. Then we have something called response time, that is the time from the request of the submission until the first response. If we are talking about one process is split into multiple time slots and worked one after other and all that, instead of the whole thing is working in one stretch like a non-preemptive scheduling, if we had something preemptive scheduling and one process is split up into multiple subtimes, and then when the process was initiated, from that instant till first time that process starts its execution, that time is called the response time. So it is crucial for interactive systems. That means when we are working with human interactions, then the moment we press some key or when we press a mouse button, we expect the response as early as possible. So the response should be as early as possible. So with that response, the human will press another button, and the human activity is so slow that the other works can be a little slower, but immediately we should get a first response. So that's what we look at response time, which is very crucial for interactive systems, and it is not same as turnaround time. Turnaround time is something from the request of submission till end of the process. So when the process completes running from till then, from the requested time, the whole time is called turnaround time, whereas in this case, when it starts executing first time, that time is called the response time. So more details about all these times and differences between them. Sometimes it may look similar, but difference between them we look at when we are working with different scheduling types of algorithms and looking at preemptive, non-preemptive types of algorithms. We understand these terms more clearly. So this type of measurement and this metric is well suited when we are working with user interfaces, real-time applications. The moment we press a key, we would like immediate response. We don't want the response to be delayed for some seconds or something that irritates the user. Now, final result may come little slow, but immediately we should feel that yes, we have been acknowledged. The moment I press a key, something should start working on the screen. It may not be the final result, but at least some intermediate results I would like to see on the screen, and that's what makes the user satisfied, and that's what user wants. So when we are working with user interfaces like that is when user is interacting with the system, then this metric is very much important. So the overall, what we have seen in this previous few minutes, throughput is the total number of processes executed in a given time. Waiting time is the time spent by the process in the ready queue. Response time is the time spent in ready queue to get CPU for the first time. Waiting in the ready queue and you get the CPU for the first time. That gap is what we call response time, and the turnaround time is the waiting time in the memory. That is then the waiting time in the queue, then the time required for execution, and the time required for doing IO. All these time together is what we call the turnaround time. More details on this as we look into various different types of scheduling schemes, and then each of these we look at and see how each of these matter and what each one mean when we are dealing with different scheduling schemes and all that. So that's it for now. Many more issues to come, so please don't forget to like, comment, share and subscribe to this channel. Thank you. Hi friends, welcome back. Now let's get into the various scheduling algorithms we have in store for scheduling the processes. This is required when we have more number of processes than the number of CPUs available, and we need to ensure that all the processes, all the threads get a fair chance to run. So that's what scheduling algorithms are. Just a glimpse of various types of scheduling algorithm. Two types of scheduling algorithms: preemptive, non-preemptive. In preemptive type of scheduling, a process can be stopped in between and another process may be accommodated, whereas in non-preemptive, once a process is allotted CPU, till end of that process CPU will be with that particular process. So the common examples for preemptive are priority scheduling, round robin scheduling, and the common examples for the non-preemptive are the first come first serve, shortest job first, and so on. So let's dive into the various types of scheduling algorithms we have, and then look at what they mean to the different situations, and then see what type of situations are better for a given scheduling algorithm, and what are problems with the scheduling algorithm, pros and cons and all that in detail one by one. So let's begin with the simplest logic, that is the first comes first served type of scheduling. It's a non-preemptive scheduling algorithm where the process that arrives first will get a chance to use the CPU first, and it doesn't matter how long it takes to run the process. So the process time doesn't make any sense here. What makes sense here is only the arrival time. The one which comes first will get the chance first to run, and it is a non-preemptive. That means once a process gets a chance, till the end it will continue to run. So the example would be a simple queue at a ticket counter. So the one who comes to the counter first will get the ticket first. Doesn't matter how long the person stays at the window, but the only qualification is the one who arrived first will get the ticket first. That's it. And the processes are ordered by their arrival time. There's nothing to do with the process time. It only matters is the arrival time, and once a process gets the CPU, it runs to the completion. So till that process is complete, it is going to continue to run. The same process will continue to run till it completes its work, and the next process in the queue starts only after the previous one finishes its work. Till the previous one finishes, the next one will not get the chance to run. A simple example would be, we have three processes, P1, P2, P3, and the runtime burst time is, first one is 24, second one is 3, third one is 3, and the figure shows here that P1 has come first, therefore P1 gets chance first. So P1 occupies 24 slots of time. Only after 24 slots of time P2 comes into picture, because P2 is the second one to arrive, and P2 runs from 24 to 27, and then P3 gets its chance, and P3 goes for 3 more time slots. Now if we want to know what is the average waiting time and all that, P1 immediately started executing, therefore there is nothing to wait. So the waiting time for P1 is 0, and P2 had to wait till P1 completes, therefore waiting time for P2 is 24, and P3 starts only at 27, therefore the waiting time for P3 is 27. So the average waiting time, if you look at it, is somewhere around 17 units of time. So the advantages of first come first served, simple to implement, fair, the processes are served in the order they arrive, so the way they arrive, the same way they will be run, and this is good for batch systems where jobs are of similar size. So usually the batch systems where jobs are of similar size, we can prefer to use first come first served type of scheduling. Yes, of course there are disadvantages with it, and there is a convoy effect. That is, one long process is going to delay all others. Just last example we have seen, the first process was 24 units of time, whereas the other two were only 3 units of time, but still the first one got 24 units of time, the other two have to wait for a very long period. So that's a convoy effect. So one long process is going to delay all others. And definitely there is poor average waiting time if the jobs vary in length, as we have seen in the previous case. The first job was of very long size, second job, third job were of small sizes. So size of each job is different, and because of that the average waiting time could be poor. And there is definitely no preemption, so it is not good for interactive systems. Just imagine that our system is working on a multi-processor, multi-process, multi-threads configuration, and any given time one process or one thread is working. And if you assume that our current system is working on non-preemptive type of scheduling, and current status of the current job, whatever it is doing, if it is taking almost infinitely long time, then you do anything, whether you hit the mouse button, whether you hit the keyboard, do whatever you like, it's not going to respond, because our processor is busy working with one process, and that one process is taking very long time. And hence, when we are working on interactive systems, definitely this non-preemptive type of scheduling is a little annoying, creates too much of irritation, because it's not responding immediately, because in the background some other process is running, and whatever process which is to run for clicking of this particular mouse or clicking any keyboard button, whatever process has to work, and that process will not come onto picture, because that will not be scheduled, as this current scheduled job is taking quite a long time. So that's going to be a highly irritating situation. So that's one issue. If the first job is too long, then it's going to create a problem to all other jobs, and because of no preemption, this is another problem we do have. So looking at the convoy effect, it occurs when a long-running process holds the CPU or a resource, causing shorter, faster processes to move unnecessarily, wait for a very long time. This is going to lead to poor CPU utilization, very low throughput, and definitely very high waiting time. So what is happening here is that the first process itself is taking very long time to run, and this is holding the CPU, or any process is holding a particular resource. Then any other processes which want to use CPU or resources for a short period have to wait unnecessarily till this currently running process completes its job, and hence the CPU utilization goes down, and definitely the throughput is low, because in a given time the number of processes completed is going to be low, and definitely each one is forced to wait long period, and hence waiting time is going to increase. So as an example, if you look at it, it is like a slow moving truck on a one lane road. So there is one lane road, and in that one lane road a slowly moving truck is going, and behind that truck any faster cars or the bikes which could have run faster than that are stuck behind it. So that's going to be a big problem, and it's what we call a convoy effect. So that's one major problem with first come first serve, because it is whichever comes first will be served first, and for some reason, or if the first job is too long, then each one is going to get affected, and that leads to poor CPU utilization, low throughput, and very high waiting time. So that's about first come first serve. other scheduling algorithms to follow. Please keep watching. Thank you. Hi friends, welcome back. Now let's get into the second type of scheduling algorithm under non-preemptive scheduling, the shortage job first. This is a non-preemptive scheduling algorithm which selects the process having the shortest CPU burst time as the next process under execution. So among all the processes which are in the ready list, it identifies how much time each process needs to complete its execution and then arranges them in ascending order as per the burst time, and then the smallest burst time process is allotted first, and then it continues like that. So to understand a better way, let's take up an example. Here we have four processes, P1 through P8, having burst times 8, 4, 2, 1 respectively. And if you look at it, the shortage job here is P4 with 1 unit of time, and the next shortage job is P3 with 2 units of time, and next is P2 with 4 units of time, and finally P1 with 8 units of time. So that's how the processes are allocated: first P4, then P3, then P2, and then P1. And what is the advantage of doing this is the average waiting time. So look at P4 immediately starts working, therefore it doesn't wait, and P4 takes 1 unit of time, therefore the next process P3 has to wait for this 1 unit of time when the CPU is executing P4. So waiting time for P3 is 1 unit, the next process is P2, and P2 waits for process P4 and P3 to be completed by CPU, so that makes totally 3 units of time, and finally P1 gets its chance after P4, P3, P2 are executed, that is 1, 2 plus 4, that is after 7 units of time P1 gets its chance, so P1 has to wait for 7 units of time. In all there are 4 processes, therefore added them, divided by 4, that gives our average waiting time, that comes to 2.75. Now let's check up when we have these processes not coming at the same time but arriving at different times. So if this happens, then what will be the scenario? So at 0 time, when we begin our scheduling system, then at 0 time we had only P1 available, and which is having 8 as a burst time. Therefore the scheduler starts working with P1, and since this algorithm is non-preemptive, therefore after 1 unit of time P2 comes up, and even though its burst time is less than the remaining time of P1, it cannot stop P1 and allot P2 because it is non-preemptive. Therefore once P1 starts executing, then for 8 slots P1 continues to execute, and by the time P1 completes it, we have spent 8 units of time, so the timer has crossed 8 units, and in this 8 units of time P2 has arrived, P3 has arrived, P4 also has arrived, because now the clock is showing 8, and P1 has come at 1, P2 has come at 2, and P3 has come at 3. Therefore at 8 all 3 P2, P3, P4 are available, and then shortage job will check the burst time and then realizes this P4 is the smallest burst time, therefore the next job allotted is P4, and now we are left with P2 and P3, both are there in the ready list, and P2 requires 4 units, P3 requires 2 units, therefore P3 gets the chance, so 2 units of time is reserved for P3, and the next 4 units of time is reserved for P2. So that's how the things happen. Now if I look at the average waiting time, then P1 begins immediately when it was arriving, so the average waiting time for P1 is 0. Now if you look at P2, then P2 starts at instant 12, that means for level instance it was waiting. Then P3 begins at instant 10, that means it has to wait for 9 minus 2, that is 7 units of time, and then P4 is at 9 minus 3, that is 6 units of time. So that's something around average comes to 6. Now instead of non-preemptive, if it was preemptive, then we would have started at 0. There was only P1, so we start with P1, but after 1 unit of time P2 arrives, and then we realize that P1 has done 1 unit of work, still 7 unit of work is available. P2 needs only 4 units, therefore P2 gets the chance, so 1 unit of time P2 is getting, and after 1 unit of time P3 comes in and it says I want only 2 units, whereas P2 wanted 3 more units and P1 wanted 7 more units, so 2, 3 and 7, so 2 happens to be the smallest, therefore now P3 gets its chance. Then at the third instant P4 also comes and it says 1 unit, so at that time P3 wanted 1 more unit, P2 wanted 3 more units and P1 wanted 7 more units, so both are 1 1, so it can be either P3 continuing or we can give chance to P4. So assume that we have given chance to P4, so P4 completes its job, and then P3 1 more is required, P2 3 more required, and P1 7 more required, so P3 wins the race, so the remaining 1 is allocated for P3 next, and then P2 wanted 3 more and P1 wanted 7 more, so 3 is more than 7, so 3 units of P2 allocated, then 7 units of P1 is allocated. If we were working in non-preemptive, a preemptive type of scheduling, in that case, if you look at it, the average waiting time would be for P1, it starts here, then not P1 working, no P1, no P1, so 1, 2, 3, 4, 5, 6, 7 units of time P1 is waiting, and P2 waits, it comes at unit 1, therefore this is not waiting, then 1, 2, 3 units of time P2 is waiting, and P3 comes at 2, therefore P3 comes at 2, immediately P3 is given a chance, therefore here it is not waiting, but it is going to wait for 1 unit of time, and looking at P4, P4 has come at 3 and immediately it gets a chance, so it is not going to wait anymore, so total happens to be 11 by 4, that is the average is 3.75. and if you look at the average response time for this, P1 begins as soon as it arrives, so response time is 0 for that. P2 arrives at 1 immediately it gets response, so response time for P2 is 0. Then P3 at 2, so at 2 P3 comes and immediately it gets the slot, so its response time is 0. Then P4 is at 3, immediately it gets, so it's also 0. So the average response time for this particular situation is 0. That's a best way. The only thing is it has to be a preemptive thing, but usually shortest job first is a non-preemptive thing. So let's look at another example. This same example we had seen when we were looking at first come first serve, and if it was first come first serve, then 21 gets chance first, then 3 gets the chance, then 6 gets the chance, then 2, and if you look at it, then the first process there is no waiting time, but second process has to wait for 21, third one has to wait for 21 plus 3, that is 24, and the fourth process has to wait for 21 plus 3 plus 6, that is 30. So in all, average waiting time was 18.75 for this particular problem. But the same problem, if we apply shortest job first, then the shortest job is 2, so P4 comes first, then 3, that P2 comes next, then 6, then P3 comes next, and finally P1 comes. And if you look at it, the waiting time for P4 is 0, waiting time for P2 is 2, and waiting time for P3 is 2 plus 3 5, and waiting time for P1 is 2 plus 3 plus 6, that is 11. So the average comes to 4.5. Now let's look at some problems associated with this. So let's take another example. Here two processes P1 P2 arrive at the same time 0. The P1 has got a burst time of 10, P2 has got a burst time of 2. So once we begin our process, then at instant 0 there are 2 jobs waiting in the ready list, P1 and P2, and P2 needs 2 units of time, P1 needs 10 units of time, therefore shortest job first scheduling says P2 should be given chance first, therefore P2 is given chance. And by the time P2 is run, 2 units have elapsed, and that time P3 has come in. After 2 units of time, P3 has arrived. So now on the ready queue, we have on the ready list we have P3 as P1, P3 needs 2 units, P1 needs 10 units, therefore P3 wins the race. So next 2 slots allotted to P3. So now we have elapsed 4 units of time, but at the third instant P4 joined our race, and at this, when we completed P3, P4 and P1 are in the race, and again P4 time is 2, P1's time is 10, therefore P4 wins the race. And by that time P5 also has come in, and it also needs 2 units, so that will win the race. So P5 gets 2 more slots, and if nothing comes later, then P1 gets 10 slots. But this whole situation is dynamic in nature, so P1, P2 we are talking about arrival time. Then maybe somewhere at 5 P6 may come in, that also say wanted 2 or 3 units of time. Then at 5 P5 has completed at 8, and at 5 P6 has already arrived. That means 3 units of time required for P6, 10 units for P1, therefore P6 will get the chance for 3 more slots. Then P1 gets delayed. Then unfortunately for P1, in another process with burst time less than 10 comes in. So if this scenario continues, and each time one process completes its job, there is another process waiting in the list which has a burst time less than 10, then it will get the chance, and the next time another one comes in, and that will get the chance, and that way it may so happen that P1 keeps waiting forever. So it may get into something like an infinite loop, wait and wait and wait and wait. So that's what we call starvation. So let's look at some advantages and disadvantages of shortage of fast scheduling. This one, as we have seen, it minimizes the average waiting time, definitely. It improves the throughput because the smaller jobs are taken first. Therefore, every now and then some jobs come out saying that I have completed, I have completed, I have completed. So if you keep looking at how many jobs are completed, so the count keeps increasing quite fast. Therefore, you will have a better throughput. Then it is ideal for batch systems. That means when one batch we have a set of processes. So before beginning this scheduling to this batch of processes, we know which process needs how much time. Therefore, it will be easier for doing it. Disadvantage: yes, burst time must be known in advance. Otherwise, you cannot say which was shortest. Now you say 10 is the first job. I don't know what happens next. The next job may be 2 units, next job may be 200 units. Don't know. Therefore, it is very difficult to say what is the best job. Therefore, all these burst time should be known in advance. That's why we call it a batch system. That's a disadvantage of working with this. If you don't know that, then as just discussed previously, it can cause starvation for a longer jobs. We have seen in the previous, P1 keeps on waiting because new processes keep coming, because we are not working with a batch system. So if we don't work with the batch system, then we are not limiting our number of processes to one particular batch, and then once you limit to a batch, then you can arrange them in order and then start working with that. So definitely each process will get one schedule, and accordingly it will be definitely solved. It will be given CPU and it gets solved. But if we have a dynamic situation, as we just discussed a few minutes back, then every time smaller jobs keep coming, then this big job which had come earlier keeps starving forever. So that's another major disadvantage we have with this, and definitely not suitable for interactive system, because interactive system is one when I press a mouse button, immediately I wish to see some reaction from the system. I need to see some changes on the screen and all that. But if the process for which my mouse is giving a signal, and if that process happens to be a very big one, then it keeps starving and that will never be addressed. So it is definitely not suitable for interactive systems. It is only suitable for batch systems and all that. And definitely it is hard to implement in general purpose operating systems. We can expect its complicated implementation and all only when we want a specific operating systems to be devised. But in case of general purpose operating systems, so definitely this is not well suited. So more details about what is general purpose operating system, what is specific purpose operating system, come in future sessions. So that's it about the. Now if you look at the performance of this type of scheduling when CPU utilization is high. If the jobs are known in advance, throughput is definitely high, turnaround time is low, waiting time is minimal, response time is moderate, starvation possible. So that's it about the shortage job first scheduling algorithm. So please make sure to like, comment, share and subscribe to this channel. Thank you. Hi friends, welcome to another session. Now let us see the shortest remaining time first scheduling algorithm. This is a preemptive version of the shortage job first algorithm. The shortage job first algorithm which we had seen in the previous session was a non-preemptive type of algorithm, and this one is a preemptive type of algorithm. It is a core concept in the advanced CPU, and the process with the shortest remaining burst time is selected for the next running. So the properties, it is a preemptive. So if a new process arrives with a shorter burst time than the one which is currently running, the CPU is preempted and the new process is given the chance. We need to have a dynamic scheduling. The scheduler must constantly keep track of remaining burst times and then keep adjusting them in the ascending order. So that's a little overburdened. The goal is to minimize the average waiting time and the turnaround time. And yes, there is risk of starvation if the processes are longer. So every time a process arrives or a process completes, the scheduler compares the remaining burst times of all processes in the ready queue and picks the one with the shortest remaining time. So whenever a new process comes in, it just checks what is the remaining time for the current process, what is the remaining time for the current process, and what is the smallest time in the list. So if the remaining time of the running process is smaller than the smallest in the list, then it is continued. Otherwise, the smallest burst time process gets in and starts running. So this preempts the current process if whenever required. So take up an example. We have 4 processes with their arrival times and the burst times 8495, arrival times 0, 1, 2, 3. And if we look at what happens at 0, only P1 was available with 8 burst time, so it starts executing P1. But at 1, P2 comes in with the remaining time 4, so it starts executing. At 2, another process with burst time 9 comes in, so at slot 2 there are 3 processes in the list. One currently running has completed 1 session, has 3 more sessions to continue, and P1 1 session taken up, 7 more required, and freshly come P3 needs 9. So out of this, P2 requires only 3, that's the shortest, so P2 continues. The third slot P2 continues, fourth slot also P2 continues. So this way the P2 completes its 4 slots at 2, 3, 4 and 5. At 5 it just checks. By that time the P3 also come at 3, and now at 5 this is having 3, then P3 is having 9, P1 is having 7, so 5 is the smallest, so P4 comes in picture now, and this is 5, this is 9, this is 7, 5 becomes 4, then 4 becomes 3, 3 becomes 2, 2 becomes 1, 1 becomes 0, till then it is smaller than 9 and 7, therefore P4 continues. And once P4 is done, then we are left with P1 and P3. P1 requires 7, P3 requires 9, so 7, 9, so P1 wins, 7 becomes 6, 6, 5, 4, 3, 2, 1, 0. Till then this P3 requires 9 and P1 requires less than 9, so P1 continues, and finally if none of them is available except P3, then P3 gets its chance. So let's look at the whole scenario. So at 0 time stamp, only P1 was available, therefore P1 starts working, and after 1 slot 7 are remaining, and after 1 slot P2 comes in, and which requires 4 units of time, so P2 is given chance because P1 needs 7, P2 requires 3, and after 1 slot P2 requires 3 more, so 3 and 7, 3 is small, so P2 again, 2 and 7, P2 is small again, 1 and 7, P2 is small again, finally P2 completes its work, and by that time P3, P4 also have joined the list, and P3 was 9 and P4 was 5, and when P4 joined it was at 3, and at that time P2 was 1, P1 was 7, therefore P2 wins the race. So fourth slot also P2 takes up and completes its job. Then comes P4, 1 slot, 2 slot, 3 slot, 4 slot, 5 slots, because as long as P4 is working, we are left with P1 with 7 and P3 with 9, which is bigger than 5, 4, 3, 2, 1, 0. So P4 continues to run. And once that is done, we are left with two more processes, P1 and P3. P1 requires 7 and P3 requires 9. So P1 wins the race. So 7, 9. So P1, then 6, 9, P1, 5, 9, P1, 4, 9, P1, 3, 9, P1, 2, 9, P1, 1, 9, P1 finally completes. P1 completes its task and it's left with only P3. Therefore, P3 continues to execute for all the next 9 slots. Now, if you look at the situation, it looks like this. So first slot P1 occupies, then next 4 slots P2 occupies, then next 5 slots P4 occupies, then next 7 slots P1 occupies, and finally 9 slots P3 occupies. So if you look at the situation, then if we look for the various times, let's look at P1 waiting. So P1 is second slot is working from 10 onwards. Then for first slot it is P1, then second slot to 9th slot it is second slot to the 10th slot it is P2 and P4. So P1 is waiting in this period, so totally 9 units of time P1 will be waiting, and turnaround time, that is P1 completes its action at 17 and P1 comes at 0, and at 0 it starts execution. That means CPU gives its chance to P1 the moment P1 comes in, therefore the response time is 0. Now looking for P2, P2 arrives at 1, therefore it starts at 1 and it completes its total thing, so there is nothing for P2 to wait, and P2 turnaround time is 4 units because it has come at 1 and completed at 5, so total 4 units of time. So its actual time is 4, turnaround time is also 4. That means P2 has got full attention of CPU and wonderfully done its job. As far as race response time is concerned, P2 has come at 1 and P2 starts working at 1, therefore response time is also 0. Now looking for P3, P3 has come at 2 and P3 starts working at 17, so 17 minus 2, so for 15 units of time it had to wait to get its chance, and the turnaround time, it has come at 2, completes at 26, therefore it takes 24 units of time to complete its work from the time it has come in. And looking at the response time, it came at 2 and it started running at 17, therefore 15 units of time was the response time for P3. And as far as P4 is concerned, it has come at 3 and it starts working at 5, therefore 2 units of time it had to wait. And then P4 completed at 10, it had come at 3, so it should have been 7, sorry. So the turnaround time is 7 units, and response time, it had come at 3 and it was recognized at 5, so the response time is 2. So the average is 6.5 waiting time, somewhere less than around 12 for the turnaround time, and 4.25 is the response time. So this gives almost best solutions for all parameters. So the advantage of using this algorithm is minimum average waiting time, efficient CPU utilization. So your CPU is never waiting for any other whenever any process goes on waiting for some IO and all that, then we can allot this. So CPU utilization is a better, faster turnaround time for the shortage jobs. Yes, the shortage jobs are given chance first, therefore the moment they come in, they possibly get the chance to run, therefore the turnaround time is as small as possible, reduces turnaround time. On the other side, the disadvantages, yes, starvation, because we have a dynamic list now for scheduling, and as the scheduling continues and if the new processes with the smaller burst times keep coming in, then the process with the longer burst times have to keep waiting and waiting and waiting, and if this keeps happening forever, then the one with the longer burst time have to wait forever. So there is a risk of starvation, and before using this algorithm we must perfectly know how much is the burst time of each task. So a very accurate prediction is required for each burst time, and it's a little difficult to make sure, because our processes usually may contain some loops and all that, and we cannot statically say that what is the number of times the loop can take up and all that. So it may vary from situation to situation. The same process running twice may take different durations to complete, depending on many issues, like human interaction, like the inputs read from the external sources, IO devices and all that. So depending on many issues, the duration of the process keeps varying, and hence it's very difficult to implement this type of algorithm, and we do have a very high overhead, because the ready list has to be updated every now and then, and every time a new process comes in picture, the whole list has to be sorted so that the shortest comes first. So the sorting has to be done at a regular interval, or every time a new process comes in or old process goes out, then the whole scheduling has to be redone and all that, and because of this, lot of overhead will be there in the shortest remaining time first type of scheduling, and it is quite high, quite a complex situation when it comes to implementation. So that's it about the shortest remaining time first scheduling algorithm. More details, more types of algorithms to continue in the coming sessions, so keep watching. If you find this session of any use, please don't forget to like, comment, share, and please join us by subscribing to this channel. Thank you. Come back to our next session on scheduling algorithms. The next issue to look at is all about priority scheduling. All the processes do not have equal priority. Some processes are more important than others, and when the important process needs to be executed, then it has to be given priority, so that other low priority processes do not delay the high priority systems. So to ensure that, we make a change in the scheduling style, which we do call priority scheduling. Here, each process is assigned a priority number, and the CPU is allocated to the process with the highest priority. So whichever is having highest priority will get the chance first, and if more than one process has got the same priority, then either first come first serve, or the shortest job, or shortest remaining time, whatever things can be applied, but priority wise it has to run. So lower the number, higher the priority in most of the cases. That means one means highest priority. So first priority should be given to process having priority number 1, then second priority with priority number 2, and so on. So lower the number, higher is the priority. And if two processes have same priority, then they may be scheduled using first come first serve basis. Then it is a preemptive scheduling, because when a low priority process is being served, because no other high priority process was available, therefore a low priority process was being run. And on the way, if a high priority process comes up, then the low priority process is preempted and chance is given to run the high priority process. So non-preemptive, if it is, then the current process finishes even if the high priority arrives. So there may be two types of priority scheduling. One is preemptive, that is the moment a priority comes, a high priority process comes in, immediately it is stopped and given the chance. Or if it is a non-preemptive type of scheduling, then whatever current process is going on, that will be completed. Till then, even the high priority process has to wait. And once the current process completes, then among all the remaining process in the ready list, whichever is having highest priority will get the chance. So two types of priority scheduling possible, but most commonly we would like to refer to preemptive type of scheduling, because when say some high priority issue comes in, then definitely we need to stop low priority activity and then continue with that. So that's what the common logic talks of. So we'll see what all various types of things are taken up in our next sessions. So let's take up an example. Here we have 5 processes, and each process has a different burst time and they have different priorities. So if it was first come first serve, then P1, P2, P3, P4, P5 will be served in this order. But if it was a shortage of first, then P2 should get the chance first, then P4 will get, then P3 will get, and then P5 will get, and finally P1 will get, because shortage of P2 with 1 unit, then P4 with 1 unit, then P3 with 2 units, then P5 with 5 units, and finally P1 will get the chance. So if it was a first come first serve, but we are now working with the priority. That means each process has its own priority. 1 means highest priority and 5 means lowest priority. So whichever process has a least value, that means highest priority, will be given chance first. So accordingly, P2 should be given chance first, then P5, then P1, then P3, then P4. So that's what it looks like. So first P2 should be given chance 1 unit time, and then P5 should get chance with 5 units of time, and then P1 should get a chance with 10 units of time, and then P3 should get a chance, and finally P4 will get the chance. Yeah, definitely if you try to measure the timings like waiting time, response time, or turnaround time and all that, definitely this may not be the best way, but priority matters here. So if I calculate these things, then P2 immediately starts, so nothing to wait, so it has got a waiting time 0, and the duration burst time of P2 was 1, therefore the turnaround time is 1, and it could not immediately it got the response, therefore the response time is 0. Then comes P5. P5 had to wait for 1 unit of time, because before P5 P2 was running of 1 unit time, so waiting time was 1 and turnaround time was 6. It finally completed after 6th instance, and response time, so after 1 unit of time it started executing, so the response time is 1. And after that priority 3 gets its chance, that is P1. Then P1 has to wait for 6 units of time, and it completes its job at 16th tick, and then the response, so P1 started working after 6 ticks, so response time is 6. After P1, P3 gets the chance, and waiting time was 16, and turnaround time is 18, and response time is 16. So you can see the waiting time, response time is almost same in this case. And finally P4 gets in, so P4 is working for waiting for 18 units of time, and its length was 1, therefore turnaround time is 19 and response time of 18. So on average, if you look at it, it is 8.2 unit of waiting time, 12 units of turnaround time, and 8.6 units of response time. And looks very bad, but in reality, if you look at that, the processes here are arranged in the order of their priorities. The top priority is on the first place, and the least priority is on the last place. And if you just go through these 3 columns, we see that the top priority has minimum waiting time, top priority has minimum turnaround time, top priority has got a minimum response time. So therefore the top priority, so as the priority decreases, these times keep increasing. So 0, 1, 6, 16, 18, so you can see that they keep increasing, and definitely it should not matter, because the highest priority is getting a better response with minimum waiting time, minimum turnaround time, and minimum response time. Of course, the low priority cases may get delayed and all that, so that should not be a major issue here, because the major issue here is who has got authority, who is more important and all that. It is like in the traffic, there are different types of vehicles moving. It may be an ambulance, it may be a minister's car, it may be a common man's vehicle. Then definitely the ambulance should get the highest priority over minister's car and even the common man's car. So the highest priority is given to the ambulance, the next priority is given to the minister's car, and finally it is the common man's car. So in that case, even a common man gets delayed, doesn't make any big difference. But yes, it makes a difference. If the ambulance gets delayed, there is chance of getting loss of life, or if it can be an ambulance or it can be a fire brigade system. So make sure to allow these vehicles at their fastest way, allow them to move, so give highest priority to them so that they can save lives. So that's what is important here. Doesn't make much sense. Doesn't make sense whether the low priority things are using more time or not. So properties, the type preemptive scheduling can be preemptive or non-preemptive. The priority scheduling, the scheduling base is process priority. Starvation risk, yes, it is very high for low priority processes. So if high priority processes keep coming, then the low priority process need to wait forever. So there is risk of starvation, and fairness can be improved with aging. Now looking at the advantages and disadvantages of working with priority scheduling. So advantages is highly flexible. You can give importance to urgent and real-time processes. Like I'm moving the mouse. So when the mouse is moved, the mouse icon on the screen is also moving, and I would expect this motion to be in real time. As I move, it also should move in sync with my motion of the mouse. But if it is getting delayed, definitely it is going to create a nuisance, and it is going to create a big problem. I think that I am pressing here, but it was stuck somewhere else, and it gets pressed somewhere else, and that's what would happen if it is not given importance. So if you want to make it urgent activities, real-time processes, then we should give high importance to them. So we give a highest priority to that, so that the whole activity can be taken up in real time. And it supports differentiated service levels, so you can think of different levels of services, and each service can be given a different priority depending on how important that service is and all that. Like kernel level services, user level services, kernel level services will have definitely higher priority compared to the user level services. Therefore, whenever kernel level services are required, then all user level services have to wait for their turn. And definitely it is efficient for time critical applications. So whichever application is time critical, then we should be given high priority, so that it works in time and all that. But the disadvantages on the other side, starvation is a big problem, because low priority process may have to wait forever. If high priority processes keep coming, then this low priority process may have to wait indefinitely, and definitely there will be starvation, and that process may never get chance to run. Then the priority inversion, the low priority processes hold the resources, but they are needed by high priority one. So what happens? We look in detail about resource holding, because we don't want more than one process to use the same resource. As we were discussing, sharing the resources is a big problem. So if any process wants to use a resource which other process also may want to use, then there is something like locking mechanism. So we just lock it and say that this resource is currently useful only to this particular process, and that process which has locked a resource happened to be a low priority process, and when a new high priority process comes in, then the low priority process will be stopped and high priority process gets to work. And unfortunately, if that high priority process wanted a resource that was already locked by the previously running low priority process, then the high priority process keeps waiting for the resource to be released, and to make the resource to release, we need to run that low priority process, which is impossible, because high priority process is given chance now. Until high priority process completes its tasks, low priority process cannot come in picture, Until low priority process cannot come in picture, it cannot use the resource and release the resource. Until that releases, the high priority thing cannot continue, and therefore it will not stop. And this makes both the process to stay in that condition forever, which we call deadlock. We look into this in detail in the coming sessions. And we need to have a very good priority assignment policy. We need to say among all the processes, which process should get highest priority, which process can get lowest priority. So there has to be some proper protocol for deciding this. Otherwise, it may create havoc. Like in the traffic, we have to have a proper guidelines of which type of vehicles should be allowed first, which type of vehicles should be allowed next, and all that. Like ambulance, fire services and all that should get highest priority. Others may wait, so depending on the situation. So there are different situations where sometimes police is important, sometimes police is not important, sometimes minister's car is important, sometimes it may not be important. So depending on the situation, it has to be decided, and that decision has to be taken in a very fair manner, and a proper backup is required for these decisions and all that. So a proper policy is required, and creating this policy is a very tough situation, and if seriously, if it is not given a thought, then we may create some imbalance in providing these priorities to the processes, and that may in turn create problems to the overall system. So that's all about the priority scheduling. Hope you enjoyed this journey, and if you enjoyed it, so please do like, comment, share and subscribe to the channel. Thank you. Hi friends, the next issue to discuss in the scheduling algorithms is the round robin scheduling. This is designed especially for time sharing systems where multiple processes want to use available limited resources on time sharing basis. Usually it is similar to first come first serve scheduling, but under preemption it works. So in this preemption is added to enable the system to switch between the processes. In the original first come first serve basis type of scheduling, the process that has come first is allotted the CPU to run, and that process will leave the CPU only when its work is done. Till then it will not allow CPU to work for any other process, because it was non-preemptive type of scheduling. But round robin works almost like a first come first serve scheduling, but preemption is there, so that while one process is running, we can stop it and make other process to run on a round robin basis. In this small unit of time called a time quantum is defined, and after every time quantum the process changes its place. So the process which is running will stop running and gets into the ready queue, and the next process in the ready queue comes back to running state, and after every time quantum this cycle repeats. So let's take an example. Only with example we can understand any concept. So let's take an example which has got three processes P1, P2, P3, and let us simplify the problem, saying that there is no arrival time in this case. Everything has come almost on the same time, and P1 has a burst time of 24, P2 has a burst time of 3, and P3 has a burst time of 3. Now if it was a simple first come first serve, then P1 will be executed, so it takes 24 units of time, then P2 takes 3, then P3 takes 3. So in all, in 30 units of time, all the three processes complete their job. But looking at the waiting time, P1 has no waiting time, P2 has to wait for 24 units of time till P1 is completed, and whereas P3 has to wait for 27 units of time till P1, P2 both are completed. So average waiting time was quite high. Now if we change this and make this whole thing as a preemptive type of thing, that means each process gets its own turn on a cyclic basis for a period of time quantum. And the advantage of this is if three processes are running in this time sharing manner, round robin scheduling manner, then after some number of quantum slices, time slices, each will get its turn. And if these processes are under the human observation, then for a small time it may not be active, but now and then it becomes active. So round the clock it becomes active now and then. But for the human, because of slow response of the human looks at the screen, understands it, and all that takes some milliseconds, but the processor is working in nanosecond. So the whole switching is done in nanosecond speed, then definitely human will not be able to understand that something went on off and all that. So human feels that all three are running simultaneously, all three are on all the time. So that's the advantage of working with round robin scheduling. Let's look how this situation is working if we work for a say time quantum of 4 units. So as usual, P1 gets its turn. After 4 units, the scheduler says P1 to stop. Other processes are there waiting, so please stop. So P1 stops, and then P2 gets its time of 4 units of time, because time quantum is 4. So for 4 units of time, P2 gets the chance, but P2 needs only 3 units of time. So after 3 units, P2 is done, and now P3 gets its chance for 4 more units of time, 1 quantum. But P3 also needs only 3 units of time. Therefore, after 3 units of time, P3 also completed. Now we are left with only P1, so we keep on giving the 1 quantum to P1. And then look, anybody else is waiting? No. Then again P1. Anybody else waiting? No. Again P1. Anybody else waiting? No. Again P1. So that way, first we start with P1, then P2, then P3, then again 5 slices of P1 will continue, because in all with one time slice having 4 burst time, then 24 burst time needs 6 slices. So P1 we can count that there are 6 P1s, 1, 2, 3, 4, 5 and 6. So 6 quantum. Now what is happening if you just look it carefully? So at the user's point of view, if user is working for P1, then the moment the system starts, P1 comes into life. And before a human could understand that P1 stopped, P2 starts. So the one who is interested in P2 sees that within 4 time slots P2 started, but these 4 time slots are so small that infinitesimally small that human cannot understand that P2 started after 4 time slices or time slots. Therefore, the human thinks that P2 also started in the same instant. Same way P3. Then, as long as P1 is concerned, P1 gets a response in the first slot itself. Then for 2 slots P1 is not working, but these 2 slots are so small for the human to notice that by the time human is able to notice, again P1 started executing. Therefore, for the one who is interested in P1 doesn't notice the gap where P2, P3 occupied. For person with P2, this small gap, a delay of starting execution, that is the response time P2 4 units of time, is almost negligible for the human. Same way for P3, the response time is 7, so that also looks almost negligible. So all the 3 processes appear as if they are running together in parallel, as if each one has their own processor, their own CPU, but in reality there was only one CPU and they are running one after other in a loop. And this gaps are so small that we will not be able to notice it. So round robin scheduling is a preemptive CPU scheduling algorithm where each process gets a fixed time slice or quantum to run. It works like a rotating turn based system and very fair and predictable. So we know that first if P1 comes, then P2 comes, then P3 comes, then P1 comes, then P2 comes, then P3 comes, and so on. If each one P1, P2, P3 are having the burst time very much greater than the time slice or time quantum, then these get repeated P1, P2, P3, P1, P2, P3, P1, P2, P3. So we know that in what order they are repeating, and each one definitely comes after 3 rounds. P1 comes after 2 more gaps, then P2 comes after 2 gaps, P3 comes after 2 gaps. So it is very fair and definitely predictable that if P1 has come now and if there are 3 processes running in the ready queue, then the P1 will repeat after every third time slice. So the type is preemptive. Decision is based on the time quantum, not on the size of the process burst time and all that. That doesn't make any sense with respect to burst time, like it was done in shortest job or shortest remaining time algorithms. Here it only depends on the time quantum, and usually done with first come first serve logic with preemption and very high fairness, because every process gets a turn in every cycle, and definitely no chance of starvation, because if there are n cycles, then in first n time slots everyone gets one chance. So in every nth turn each one will get a chance. Therefore there is no question of any process being starved. So looking at the advantages, it is very fair and simple to implement, excellent for time sharing systems, and it prevents definitely starvation, and good response time for interactive tasks, because it's everyone is getting a share in a round cyclic way. So the interactive, when you say that human is working with that, like pressing a mouse button or typing something on the keyboard, and the speed with which human is working and the speed with which the process is working is almost quite different. Therefore the speed with which human is interacting, in that many time quantums can be used for some other processes without the user noticing that the system was not available to the user for some time. Coming on the disadvantages side, the performance heavily depends on the time quantum. What is the time quantum? How much it is? So if it is small, what happens? If it is large, what happens? That's what the problem with. Let's see what it means very soon. So too many quantum switches if the time quantum is too small, and definitely not optimal for batch system. So if you are talking about batch processing, then this one is not optimum. So the properties, round robin performance, if you look at it, CPU utilization is moderate. That depends on the quantum. We'll shortly look how it varies. Turnaround time is moderate, waiting time is low if short jobs are there. Response time is good because each one almost immediately responds. That means if there are n processes in the ready queue, then the response time can be maximum n-1 times the time quantum. That is the last in the loop. So that is n-1 times it may have to wait for getting its turn. So response time is very good. Definitely no question of starvation, and yes, preemption is required for that. Now the issue is effect of time quantum on our performance. If the time quantum is very small, then what happens? Every now and then the process has to change. So context switching, which means switching the CPU allotment from one process to another process. So if it is the time quantum is too small, let's say 2 milliseconds, then after every 2 milliseconds the process has to change. So what do you mean by changing the process? As we discussed in the initial period of the process management, there is a process control block, and that process control block has to be updated every time a context switches. So too many context switches, then every time a new code has to come onto the main memory, every time it has to change the program counter, the various other register values, and all that has to be modified. So that calls for very high overhead and definitely very poor CPU performance, because most of the time it is busy in copying in the new process and copying out the old process. So getting in the new process and getting out the old process, this is a major work than actual processing. Therefore the CPU is wasting most of its time just in copying the context in and out. And definitely a fast response time, because the time slice is very small. Then if it is 2 milliseconds, then if there are n processes in the ready list, then maximum 2n milliseconds required for responding to any process. Yeah, that's the only positive part of this. If the time quantum is too small, the going to other end, other extreme, if it is too large, like 500 milliseconds or so, definitely context switches size are very small, so we can say it is efficient compared to the overheads and all that. We have very few overhead, and because you are not wasting time on writing, rewriting and all that, so definitely our CPU time is being utilized for executing the actual code instead of copying in and out the context switchings and all that. So it is better if we have too large time quantum, but our problem is it just looks like simple first come first serve logic, and definitely very poor response time for short or interactive tasks. If the task is very short, and if it happens to be at the end of a third or fourth or fifth position, then after 3, 4, 5 times 500 milliseconds only it gets chance to come up first time. Therefore very long response time is there for that, so it is very poor in terms of response time, and definitely not suitable for interactive tasks, because the one task is getting 500 millisecond, then second one gets 500 millisecond, third one gets 500. Say if my changing this mouse is a attempt in that loop, then after every 10 rounds my motion or my mouse movement is observed. That means 10 rounds, that means after every 5 seconds my mouse is observed. So for 5 seconds it looks here, after 5 seconds suddenly it jumps here, then jumps here, then jumps. So it doesn't make you feel that it is moving with my hand movement, but I try to move the hand movement, but till 5 seconds it is shown here itself, but after 5 seconds suddenly it jumps here, and that makes it too irritating for the user, and definitely is not for interactive tasks. Now you can think of something in between, so which we can call optimal time quantum, maybe 10 to 100 milliseconds. So it is 10 to 100 milliseconds is not too small to have large number of context switches, therefore overhead is not very high. So there is a very good balance between CPU efficiency. So this was having a very good CPU efficiency, and this was having very poor CPU efficiency, and this was having a good CPU efficiency, this is having good response time. So it's a balance between good CPU efficiency and good response. So that's what we can think, and smooth multitasking is possible, and very good user experience we do have, because in 10 millisecond it is changing its position, and 10 millisecond is so small that we cannot notice that for 10 millisecond our mouse pointer did not change its position. So after every 10 milliseconds or 100 milliseconds it is changing its position, then we will not be able to notice it, and that makes things smooth changing, and it have a good user experience and all that. So that's all about the scheduling algorithm, which we call round robin scheduling algorithm. So hope you enjoyed this journey. Please do like, comment, share, and please subscribe to this channel. Thank you. Hi friends, welcome back to another session. Now let's see what a multi-level queue scheduling is. So multi-level queue scheduling divides the ready queue into multiple separate queues, where each queue has a specific priority or job type and uses different scheduling algorithm. Processes here are permanently assigned to a queue based on their characteristics, like the process may be a system process, or it may be an interactive process, or it may be a job process, and so on. And each process may have a different priority, like the system or kernel process may have highest priority, and the interactive process may have moderate priority, and background or the batch processes may have least priority, and so on. And each of these processes may use different scheduling algorithms, like kernel processes may use a high priority round robin method, then the interactive can have a round robin, and the background or the batch processes may use first come first serve, and so on. So here we have various types of processes we can look at. So the highest priority is given to the system processes that run under the kernel, and then the next priority is given to the interactive process. That means where a human is interacting with the system, and that has to give immediate attention. But of course it is not that important as of kernel process, therefore it important, but not that important as a kernel process, so it has given the second level priority. Then we have interactive editing processes like word processor and all that, where we keep typing and all that, and we would expect whatever we type should be visible on the screen at the earliest, therefore should be having a higher priority, but definitely not as high as interactive processes or system processes, so they take a third level. Then we have batch processes, where a batch of processes do, and there is no need for getting the work done at the earliest and all that, so there may be a delays and all that can be tolerated with such processes, and therefore they have a lower priority, and so on. So if you look at the positive part of working with multi-level queue scheduling, so we have very clear prioritization. So the critical tasks like system processes always get first attention. So flexibility, so different algorithms can be used per queue. So it may be round robin, it may be first come first serve, it may be shortest job first, etc. So different queues can have a different algorithms, not necessarily that all the jobs in the system should work with only particular scheduling algorithm, and so on. And as far as efficiency is concerned, it keeps the system responsive to the real-time and interactive task at the earliest, and the slow processes may be delayed, but the one which needs immediate response are addressed immediately, almost at the real time, therefore it will be highly efficient. Now looking at the negative side of that, that's starvation is a major concern here for low priority processes. So low priority processes may never get the CPU time, because every time a low priority process tries to get the CPU, some high priority process may be available in the higher queue, therefore this low level processes may never get chance to run, and hence will have a starvation. And there is a also problem with the rigid design, that once the process is assigned to a queue, then the process cannot be switched from one queue to another queue. So at the time of allotment, any new process comes in, then we have to decide exactly to which queue it should belong and should be assigned to the appropriate queue. And if something goes wrong in allotting the queue, then it is not possible to change in future. So by mistake, any critical process is given a lower priority, then it's going to create a major problem in future. Or by mistake, if any system, any process that's going to take too long, and if by mistake if it is allotted a higher priority, though delaying that may not cause a major problem to overall system efficiency, overall commute and all that, but still by mistake if it is given a higher priority, then it will disturb definitely other processes that were more important, more urgent than this particular one. So even if we understand that something went wrong, it is not possible to correct it once a process is assigned to a particular queue, and because of this rigid design, it is not possible to change the process from one queue to another queue. And a lot of complex setup is required, a very careful queue design is required, and very complex classification algorithm is required to identify the importance of every process and to ensure to which queue the current process to be assigned, so to which queue this particular process should be added to. So that it's really a great challenge in making things work perfectly. So a lot of challenge we have in designing queue designs, that is identifying to which process to be added to which queue and all that. So that's some details about the multi-level queue scheduling, and that's it for now. Thank you. Hi friends, welcome back. In the previous session we had seen about the multi-level queue scheduling, where we had multiple queues, each queue having a separate priority, and processes, whenever they come, the importance of that process is somehow identified and made to sit in a particular queue, and the scheduling is done as per the priority. And another difference was the different queues may work on different types of scheduling. So something may be round robin, some may be on the first come first serve basis and all that. But we had a problem there, that is identifying the correct queue to which any process belongs to. And if something goes wrong in identifying, and it is going to definitely create a big problem in the system. So we need some way out of this. So example, at the time of deciding which queue a given process should belong to, and by mistake an unimportant task is given high priority and an important task is given a low priority by mistake, then a not very important task goes into the high priority queue and the important task may go into the low priority queue, and so on. And while the scheduling is done, then the first preferences are given with the processes that are in the high priority queue, and hence all the processes in the high priority queue get the chance before the processes in the low priority queue. But by mistake, some process that is not very important is in the high priority queue and it gets chance to run first. But may happen that a process with a high priority having more importance was wrongly classified as a low priority process and hence put in the low priority queue. And what could happen is that the low priority process, which was supposed to be in the low priority queue, has gone into high priority queue, so it gets a chance to run earlier. And if it is going to take too much of time, then what could happen is the really important task, which was misclassified as a low priority task, keeps waiting till this unimportant task is being executed which is taking quite long time. So we need some way out. So it is very difficult to decide at the time of classifying which queue the given task should belong to, but we should have some means to modify the position of the process. So we should be able to change the queue from one queue to another queue and so on. So like if unimportant task by mistake went into high priority queue, then we should understand that there is something wrong. It is taking unexpectedly long time to complete, and we should somehow make it go down onto a lower priority queues. So we should be able to shift them to the lower priority queues. And other side, low priority queue tasks, if they are not able to get attention of the CPU for a very long time, then there should be some way out. Instead of keeping that process star, we should somehow make it visible to the CPU, and this we can do by shifting this process from a low priority queue to high priority queue. So we can upgrade the priority queues for long pending cases, and we can downgrade the priority queues for the processes which are unnecessarily wasting the CPU time and all that. And that is what is the main idea behind multi-level feedback queue scheduling. So the feedback is the one which is the important thing here, and what feedback means here is to learn with time. So just keep changing the priorities as per the requirement. So the system here watches the process and adjusts the priority of that process accordingly. So promoting it if it is waiting for too long, or demoting it if it is wasting CPU's time and all that. So that's what we have with a multi-level feedback queue scheduling. So this uses multiple queues, and each queue can be different, can have different priority, and can have different scheduling strategies. And most important thing is here, this can allow process to move between the queues based on their behavior. Like if the process in a high priority queue is wasting CPU's time, then its priority can be reduced. Or if a low priority process is waiting for a very long time, then instead of keeping it star, we can just upgrade it and move to the higher priority queue. So here that is possible, and this movement is based on the behavior, and behavior we get from the feedback. Here the feedback means the system learns about the process behavior while it runs, and this will help the operating system treat the interactive and batch processes totally differently. So how does this scheduling algorithm works? So whenever we are talking about multi-level feedback queue scheduling, then we do have multiple ready queues, and each queue has a different priority level. So if we say queue 0, Q1, Q2 and so on are the queues, then queue 0 will have highest priority. That's as per our convention. So whenever a new process comes in, and whenever a new process begins its journey, it has to go into a ready queue. But there are many ready queues, so it gets into the ready queue which has got the highest priority. And if this process is running very slow, so for every process a time quantum is decided, and within that time quantum we expect that to complete its task. So the time quantum varies from the queue to queue. So from the highest priority queue, the time quantum may be small, and the lowest priority queue, the time quantum may be large. And depending on that, so if it is at the beginning, it gets into the first topmost priority queue whose time quantum is smaller, and we expect that the top priority jobs should complete their task as soon as possible, and that's what the priority is all about. So we want slowly moving things to be given low priority, we want a fast moving things to give high priority, so that the throughput, CPU utilization and all are good. But if the time quantum is complete, then we understand that this process is not suitable for this particular queue, so it is moved to the next lower priority queue, and that way it continues. On the other side, from the bottom side, if you look at it, if you find a process which is waiting too long, so since very long time it is not getting a chance to get the CPU's attention, that means it is under starvation. So to prevent starvation, it will be promoted to the higher priority queue. So this is happening through the feedback. Just observe what is happening. Anything which is on the top priority queue and not able to utilize the things as per the requirement, then it will be demoted, and any process which is unnecessarily waiting for its turn to come, then it will be promoted to the higher level, so that starvation can be reduced. And the other side, any process is wasting time of the CPU resources and all, then its priority is reduced, demoted, so that the overall efficiency, overall utility, overall throughput is maintained high. And here the each queue can use different scheduling algorithms, like some queue may use round robin at the top and first come first serve at the bottom queues. So looking at the advantages and disadvantages of this type of scheduling algorithm, it's very good for responsive interactive processes. So interactive processes will get a high priority, so they get into the higher queue and will respond immediately. And it is also efficient for long running batch jobs, because they are put on the lower end. And adaptive, main important thing is there is where the things can be modified with time, so nothing static, it is dynamic in nature. So the priority of any process can be dynamically modified depending on the behavior of the process. And it is fair enough, because it prevents the starvation with the aging or promotion. That means aging means going it down, promotion means making it up. Yeah, nothing comes freely, so it is too complex to implement and tune. Yeah, that is a big problem. So now the question comes here is what are the parameters to consider for upgrading or degrading any process from one priority queue to the another priority queue. So a proper conditions have to be put forth, so it is too complicated, and it requires careful setting of how many queues are required. That's the first place. So the number of queues depends on the situation. If the number of queues is too large, we have one problem. If the number of queues are too small, then we miss the advantage of multi-level queue scheduling. And if they are too large, then deciding which queue to come first, which queue to come again will be a difficult thing. Then deciding the time quantum for each queue is another challenge in this type of scheduling. And rules to promote the queue from the process from one queue to the upper queue, or age, that is demoting from the high priority queue to the low priority queue. So what are the conditions they should fulfill, any process should fulfill to declare itself that it is being starved, so that it will be elevated to the next priority queue? Or who is going to decide, and how any process is going to be decided that it is not fit to live in the high priority queue, it should be downgraded down to the low priority queue and all that. So finding these rules and all are quite difficult. So if you find this interesting, so please do like, comment, share, and please subscribe to this channel. Thank you. Hi friends, welcome back to another session on operating systems. Now we are into the second module, where we are looking at process management. In that now we are into the scheduling. Previous episodes we have seen about process scheduling, and now it is time to look at thread scheduling. Thread scheduling is a mechanism by which the operating system decides which thread to run next, just like a process study, but at a finer level of granularity. Threads are lightweight units of a process. A process can have multiple threads, each of its own execution path, but all the threads of a process will share the common memory. So thread scheduling is how the operating system decides which thread from which process should run next on the CPU. So some differences between process scheduling and the thread scheduling. So in terms of unit of execution, if it is process scheduling, the whole process will be scheduled at a time, whereas in the thread scheduling, individual thread of any process will be scheduled. So at any given time, the CPU is allotted to the whole process if it is process scheduling. So the process may consist of many threads, but the operating system doesn't bother about what happens with the CPU, which thread of the process is currently executing, and also the operating system only bothers that it is so such process is executing, and on that process which thread is executing, so it is not a problem of the operating system. Whereas in the thread scheduling, the individual thread is given a chance to run. In case of context switching, if it is a process scheduling, the context switching is very costly affair because the whole memory has to be changed, the state of the processes have to change and all that. But in case of thread scheduling, nothing like that, so there is no change of memory required because the thread is sharing the memory of the process itself. Therefore, when the context is switched from one thread of a process to another thread of the same process, then we don't have to change any memory because all the threads are sharing the same code, all the threads are sharing the same data, all the threads are sharing the same files open. Therefore, there is no need to change anything on the memory. That's an advantage of working with thread scheduling. In case of speed, if you look at it, then process scheduling is slower because a lot of exercise it has to do before changing the process. Whereas in the thread scheduling, it is very fast because you don't have to change anything on the memory. Just say that now onwards this thread will get the CPU's attention and all that. As far as the shared memory is concerned, process scheduling doesn't have anything to share, so two processes do not have any common memory. But thread scheduling, yes, all the threads of a particular process will share the memory. Now, why do we require thread scheduling? Is a common question we ask. So that is required to maximize the CPU utilization by switching between the threads. Enables parallelism on a multi-core processor. So if we have a multi-core processor, then each thread of a process can be given to one of the cores so that all of them can concurrently execute, and hence the overall process gets executed at a faster rate. And ensures fairness and responsiveness between the threads, especially when the graphic user interface, IO or server apps are there. So we need immediate response. So the user or the slower IO devices should feel that the processor is always attentive to it, and this can be done through the thread scheduling. So basically there are two types of thread scheduling. One we call user level thread scheduling, which is managed by the thread library or the user program. And example is pthreads and Java threads. And there's another one which is the kernel level thread scheduling, which is managed by the operating system kernel. So when it is a kernel level threading, then the operating system kernel takes care of scheduling and all that. So the example Linux kernel threads or Windows threads do use kernel level threads. So more details about this. So user level thread scheduling, so done in user space, not visible to the operating system. So whatever scheduling is done at the user level, it is done on the user space only, and one of the threads is selected and given to the kernel, thread and say you run this particular thread. So how the thread is selected, how many threads are there in that process, all are invisible to the operating system. So kernel doesn't understand what is there in the user side. Whichever thread user says to execute, that will be attended by the kernel thread. And faster context switching, because everything is done at the user level. But problem is, if one thread blocks, all threads in the process will get blocked, because user is scheduling, and if it schedules one process, one thread to a kernel thread, then kernel is attending only to that thread. And if that thread gets delayed, and if that thread stops working, or if it is blocked for some reason, then no other thread can continue. On the other end, kernel level thread scheduling, the operating system manages the threads directly. So the operating system knows how many processes are there in the current scenario, and each process, how many threads are there, everything is visible to the kernel, and then the kernel will schedule these threads. So there is a true parallelism is possible on multi-core processing environment, because operating system itself is looking at how many cores are there on inside, and how many processes and how many threads are waiting outside, and makes a connection between the user thread to the core, and through this true parallelism can be achieved. And it is better for multi-core, multi-threaded applications. If we work on the kernel level, then multi-core and multi-threaded applications do well under the kernel level thread. Now, scheduling models, as we had seen earlier, there are three types of connectivities, because we have on one side user level threads and on the other side kernel level threads. So how they are connected? So one option, there are many user level threads and there is only one kernel level thread. So many to one, one to one. So each user level thread has its own kernel level thread. So it's usually used in T-threads of Linux. And many to many, there are multiple user level threads and they are mapped to the multiple kernel level threads. So there is a pool of kernel level threads and there is multiple user level threads are there, and there is a proper mapping is done, so you can execute faster. So then the thread scheduling is important. So in web servers serving multiple clients, in parallel computations, in GUIs, especially background threads are for responsiveness. So even your some processes or some threads will be running in the background, and whenever their operations change or whenever they get a response and all that, so they want to get into picture. So thread scheduling allows the background threads to show their presence whenever they need to. And in real-time systems, thread must meet the deadlines and all that. So to understand how this thread scheduling is used, so let's check the example of a web server. Here, web server uses say thread 1, which is listening to the clients, thread 2, which serves the HTML page, and thread 3 is serving some database queries. So whenever a client wants the service of the server, then the client sends a message to the server, I want to use the server. And if the server starts attending to the client, then the next client coming with a request will not be noticed. So to make sure that all the requests are properly responded, so what we can do is, whenever a request comes from the client, one thread is created and it is attached to the client. So first thread is only waiting for the requests. So whenever a new client comes up with a request, then second thread 2 is created and it is taking care of the client's problems. So it may be just showing the pages and all that, then it will work for HTML and all that, static page and all that. But if a client also wants some data which you need to look from the database, then we can have another thread which works on the database query and all that. So overall, we assume that our system is having 3 threads. One thread is just waiting for the clients, and if the client comes up and asks for some pages to be displayed, whenever the client comes up, the home page of the website has to be displayed. So for that, some HTML file has to be worked. So the first thread 1 will create thread 2, and that will start serving HTML. And during that, if the client asks for some data and all that, then another thread is created, and that is querying the database. So thread 1 is busy looking for new clients, and thread 2, after the client has come up, is serving for the web pages and all that, and thread 3 is looking for the data. So say another client comes up, then thread 1 gets activated and it creates one more thread for another client for giving service. It may be another HTML serving, or it may be a query from the database and all that. So that way it keeps going on. So here the operating system scheduler picks among these based on some policy, it may be priority. So which is important here? Yeah, definitely thread 1's working is most important. So as long as no client comes up, thread 1 may rest. So it may go into background and just keep waiting. And the moment the request from the client comes, then thread 1 has to get immediate activity. So it has to come to action immediately, and then that's where priority comes into picture. And then we should feel that every client is given a fair chance of working with a web server, so that this thread 1 will ensure that everyone gets immediate attention. So whenever a client comes up, the highest priority is given to thread 1. So immediately it comes up and asks what you want, and the client will say I want something. Then accordingly, either HTML server or a database query server is created and attached to that client, and the client thread 1 again starts waiting. So that's what thread scheduling is all about. So that's it for me. This is Sandeep signing off. Please do like this video, share the video with your friends. Please do comment whatever you feel about the series, about the current video, and please do subscribe to this channel. Thank you. Hi friends, welcome back to yet another session on operating systems. Now let's continue our discussion on the scheduling. We were on thread scheduling. Under thread scheduling, we do see what a contention scope is. The contention scope defines to what level of threads a thread competes against CPU time during scheduling. So when CPU is being scheduled, then one thread will compete with other threads, and to what level it competes is what a contention is. So basically we have two types of contentions. One is a process contention scope, and the other one is system contention scope. In the process contention scope, the threads within the same process compete with each other to get the CPU time, whereas in the system contention scope, threads from all processes in the system compete with one another, and that's the difference. So here, when a thread wants to get the attention of CPU, then who all are in competition in the race. If all the threads in the same process are in the race, then we talk it as a process contention scope. But all threads in the system, if they are to be competed for any thread to get the CPU attention, then we call it system contention scope. So look at little detail about the process contention scope. Here the user level threads compete with each other, and this scheduling is done by the thread library, not the operating system. So at the user level we have thread library, and this thread library manages the scheduling of the threads under one process, and only threads in the same process compete with each other. The two threads belonging to different threads do not come in picture here. All the threads who are competing under process contention scope should belong to the same process. And here the operating system sees only the process as a single schedulable unit. Inside the process, all the threads are invisible to the operating system. So to the operating system, only the process is visible, and from inside the process, the thread library will select one of the threads and allow the operating system to see it. So only through the thread manager, thread library, the whole thing works here. Operating system has no role to play in this type of contention scope. So the example used, the green threads in the older Java systems or the custom scheduling frameworks are the one where all scheduling is done at the user level. The other one is the system contention scope, where it is used at the kernel level threads, and the operating system scheduler decides which thread to run. And here threads compete with all the threads system wide. That means there may be multiple processes wanting to compete with each other, and each process in turn may have multiple threads. So each individual thread of all the processes are now eligible for competing to get the attention of the CPU or core of the CPU and so on. And this can allow a true multi-core concurrency, because all threads are open for competition. All the threads of all the processes are open for competition, not like the earlier one where the competition is done only within the process. So only one of the threads within a process comes out for execution, but here all threads are available. So any thread among the current situation can use any core of the processor. Therefore, if we are talking about n core processor, then n threads may be attached to these n cores, and these n threads can come from any process, can be from one process. All n threads may be from one process or maybe from different processes, doesn't make any difference. That's the advantage of working with a system contention scope. So the example here is a POSIX threads on the modern Linux system, or window threads and so on. So that's the two types of contention scopes, and that's it for now. Thank you. Please do like this video, share the video with your friends. Please do comment whatever you feel about the series, about the current video, and please do subscribe to this channel. Thank you. Welcome back to another session on operating systems. We are into our second module, process management, in which we have been looking at the various scheduling algorithms where we have multiple processes or threads available which are to be attended by the CPU, and if the number of CPUs are less than the number of processes or the threads, then some way the processes have to be scheduled. So in the previous sessions we have seen when we have a single processor how that can be done. Now let's get into a system where we have multiple processors. That's what we have been achieving because of improvement in the VLSI technology, and also the chip size is reducing, and because of which the same processor, we have multiple cores possible, and even we are not happy with a single processor at any given time, so we would like to work with more than one processor in parallel so that the overall activity can be speed up. So various reasons are there. So for all that, what we do have today is multiple processes are available, and we have multiple processes are to be scheduled over these multiple processors. So let's see what this scheduling is all about. So multiprocessor scheduling is how the operating system schedules the processes or the threads to run on more than one processor or the CPU core. So it may be multiple cores of CPU in one chip, or there can be multiple chips, each may be having a single CPU core or multi-core. So there are many versions available. So when we have such a situation, that means when we have more than one processor available for working with the jobs, then how to allow these jobs to be run by the processors is what we are looking at. The major challenges we would like to look at while working with multiple processor scheduling is how to distribute these processes or the threads across all the available CPUs. So when a new process comes up, then to which CPU or to which core we should attach that process or the thread. So that is our first challenge we do have. So how to distribute all the current processes on the ready queue to various processors available, that is our challenge. And the other challenge is, yes, one is distributing, and while distributing we should ensure that the load is also balanced. So we are not sure at the time of allocating a CPU to any process that how long the process is going to run and all that. It all dynamic in nature. There is nothing predefined that this process is going to run for this unit of time and all that. So we don't have any such information in advance, and because of that it becomes very difficult to ensure that all the CPUs get a equal share of jobs, so that all CPUs are either not overloaded or not waiting for any job to come up. So they should have some reasonable number of jobs at any given time. So to ensure this load balancing is another challenge we do face when we are working with a multiple processor environment. And we need to ensure that the contention and the overhead is to be minimized, because when we are working with multiple processors and then we are scheduling it, and say that if we are working, say, on the round robin type of scheduling algorithm, then at any given time the job was allotted to one CPU, and after its term is over, then it is sent back to the ready queue, and next time when it gets a chance, what is the guarantee that it gets the same CPU next time? So it may get some other CPU. Then the problem with this is the processor which was having already working with a particular job was knowing all the details like the data, the program counter and all details were there with it. That is a process control block details, everything was available with that processor. Now next time if it is allotted to some other processor, then this whole thing has to be reloaded there, and that may take extra time and all that. So that will be overhead, and that has to be made minimum. Then the another issue is about how to handle the shared resources and the private resources. So each process has its own private resource like memory. Then when a process opens a file, then that file has to be available only to that process till that process completes its job. The file should not be allowed to use by some other, otherwise there will be overwriting of the data, and that may create inconsistency in the data. So not to have such problems, we should have a private access to the resources. And when we have such situations, and when these are being addressed by multiple processors, we do face many challenges of having shared resources and all that. If the whole thing is under one chip, yes, we can share the cache memory and all that, but if they are on the different chips, then we have to refer to the primary memory for sharing and all such issues. So that is another problem we do face. Then coming to the types of the multiprocessor system. Coming to the types of the multiprocessor system, we have two main types, that is symmetric multiprocessing and asymmetric multiprocessing. If we have a different physical processors in different chips, or it may be a multi-core processor on the same chip. So if we are talking about different chip processors, then symmetric multiprocessing is one where all processors are having equal rights and the same operating system. They share the memory and they share the scheduling type and all that. But in case of a symmetric multiprocessing system, there will be one master processor and that controls all other processors, and this is simple in implementation, but it is less flexible. And the third one is a multi-core processor, where multiple cores are there on the same chip and they share the cache memory and the memory buses which are there inside the processor, and these memory buses inside the processor are working at a highest speed. Therefore, the operations performed, communication among these cores are done at the highest speed, and they share the cache memory, which is again working at the processor speed. So the activities do happen at a highest speed possible. Now the various approaches for scheduling. One is the load scheduling, where we say that it's a global queue we have. Here all CPUs are pull the task from a common queue. So there is one common queue where when any process or a thread comes up, it is put on the queue, and whichever CPU becomes free, it pulls the next available process from the queue. So it is simple, but definitely can lead to cache misses and synchronization overheads, because as we discussed in a few minutes back, that if we are talking about round robin like thing, then the task once was being performed by one CPU, and next time it may be performed by some other CPU. Then the data sharing from one CPU to other CPU will take an extra time, so it's going to be an overhead. Synchronization will become a problem, and definitely the one processor is working, then it has its own cache memory, then the data required or the process code required for the next few steps are dumped onto the cache memory of that particular processor. But the next time if it is scheduled to another CPU, then we need to make sure that all the things are rewritten properly onto the another processor's cache memory, and a proper synchronization has to be taken care. So it's going to be a little costly affair when we work with a global queue. Otherwise, what we approach is processor affinity, that is you just one process is connect to one CPU, no matter how many other CPUs are available, you just pin one processor to one CPU. So in that what happens, whenever that CPU is free, that process will be running. The benefit is this cache performance will increase, and there won't be any migration from one processor to another processor and all that, so that can be saved. But only the problem is load imbalance. That means this particular process is waiting for a particular CPU to become free. Though all other CPUs are free, this process cannot run because it is attached to one particular CPU. Therefore, as long as that CPU is available, this process cannot continue further. So there will be a problem in the load imbalance, because some CPUs, though in the beginning the load sharing is done properly, but we are not sure how long each process could run. Therefore, some process may exit early, some process may run for a longer period, and if some process attached to a particular CPU run early and that CPU is now idle but cannot work because it doesn't have any CPU attached, any process attached to that CPU, though many processes are waiting for their turn, but they are attached to some other CPU, so cannot continue. So this creates an imbalance in the load. Another type is the load balancing type. So it's an extension of the previous one. Here, when we know that one particular CPU is overloaded and other CPUs are idle waiting and not having any other process to work, then this overloaded CPU can be relieved by shifting some of its work to another CPU, so which we can call work stealing. So through this, what happens is the load gets balanced. So because of this, all CPUs regularly will be getting almost equal amount of work, and that ensures better CPU utilization. And this is commonly used in the modern systems like Linux and Windows. Then we have another type of scheduling possible, which we call gang scheduling. Here the related threads and processes together are scheduled. So all the processes which are related together are scheduled together. So that's gang processing. And because of they have some similarity, they work together, they can work in parallel, so the synchronization overhead can be reduced through this gang scheduling. It is often used in the clusters. So overall, if you just look at the comparison among all this, so the load sharing, the first one, which is going to use a global queue for all the CPUs. The positive side is it is simple, it is fair. The negative side is lot of overhead and poor cache locality. Then second one, we say that pinning a particular processor to a particular CPU, that is processor affinity. Here we pin threads to a specific CPU will provide good performance, but there is a risk of load imbalance. The third one is to overcome this risk of load imbalance, we thought of having load balancing scheduling, where the overloaded CPUs are relieved by moving the task from them to idle tasks, idle CPUs. So this keeps all the CPUs almost busy all the time, but requires a very smart algorithm to identify which CPU is overloaded, which CPU is idle, and all that, and how to manage the whole thing. A smart algorithm is required. And finally, we have gang scheduling. Here the related threads are run together, and it is ideal for parallel programs and definitely needs a lot of coordination. Otherwise it's going to create large problems. So that's something about multi-process scheduling, some overview about that, and that's it for now. Thank you. The two types of multiprocessing systems. So to begin with, what is asymmetric multiprocessing, that is AMP. In this one processor, which is called a master, controls the system and assigns tasks to other slave processors which perform only the specific duties. The processor which is controlling we call the master, and others we call the slaves. The slaves will perform all the duties that is assigned by the master. So here one master CPU runs the operating system, handles all the I/O and manages the system. Other CPUs perform specific tasks assigned by the master. So they have a very small part of operating system that is sufficient to just communicate with the master and then take up the assigned task. The major activity is taken up by the master CPU, which is going to run the complete operating system. All I/O activities are handled by the master, and the overall system is managed by the master. Here the processors are not equal in capabilities or responsibilities. Major responsibility, major capability is with the master, and slaves have a minor one. So working with asymmetric multiprocessing, the advantages are simplicity in design. The operating system complexity is reduced because it has to work with only one CPU and others just follow it. Easier to predict the behavior, good for real-time systems because we are working with only one CPU, and the behavior of that CPU, the overall performance of that is easily predictable, and hence it is good for real-time systems because the prediction and all can be done at a faster rate. So then it is efficient for fixed task systems like embedded controllers and all that. The disadvantages on the other side, it cannot be scaled. One master becomes a bottleneck. So if the master is busy for something, then everything have to wait for that. inefficient CPU usage because the master CPU is always busy, and some CPUs may not get their chance at all. So some slaves may not get the chance, some slaves will get the chance. Master CPU always busy. So inefficient CPU usage and poor fault tolerance. If master fails, the whole system fails. So even if all the slaves are perfectly working, with no master working, everything just breaks down. So that's a problem with the asymmetric one. And we can't dynamically balance the load because there is only one master, and the master will statically allot the load to each of the slaves, so no chance of dynamic balancing the load. On the other side, symmetric multiprocessing, all processes are having equal power. Each one runs the same copy of the operating system, can execute any task, share access to memory and I/O. That means one process is there and multiple processes are there, then the copy of operating system is available to each processor, and each processor can execute any task of the operating system. All the processors can share the same memory and I/O. So that makes things real parallel processing, and all CPUs have equal access to the memory, I/O as well as the operating system. Shared memory system, it works with a shared memory system, so same physical address space is used by all the processors. No logical addresses, the same physical addresses are being shared by all the processors. So any processor can run the operating system or any user task. So there is no restriction in which processor should do what. So any processor can take up any part of the operating system activity or can take up any user task. And the operating system here schedules the task across the CPUs using some symmetric policies. Now looking at the advantages, load balancing, the task can be dynamically spread across the CPUs. If you find that some CPUs are having additional load, then they can be shifted to other CPUs. Fault tolerance, even if one CPU fails, other CPUs can continue working because all the CPUs are working on the same operating system, all the same CPUs are working on the same memory, all the systems can be working on the same process, all the system can be working on the same data, all the systems can be using the same IOs in parallel. Therefore, even if one CPU fails, other CPU can continue executing that task. So there is very good fault tolerance possible with symmetric multiprocessing. And we can have a better performance because true parallel execution is possible here. So when we have multiple processors, then each processor can take up its own share of the activity, and parallelly each one can run, so the whole thing can be executed much faster. And simplified programming, because same code can run on any CPU, therefore the whole programming can be simplified. Other side, disadvantages. So shared memory contention, multiple CPUs accessing the same memory can cause bottlenecks. Yes, because at the same time two CPUs cannot be allowed to use the same memory, so there has to be only one CPU using any memory, so that if they try to multiple CPUs try to use the same memory, then that may cause a bottleneck. Cache coherence complexity, so maintaining the consistency across the CPU caches becomes a problem because the cache memories are inside the CPUs, and the CPU is working with one process, and then the data and the code associated with that process are stored inside the cache of that CPU, and after say time sharing and all that, if the next time another CPU gets chance to continue the execution, then all the data, all the information available in cache of one processor has to be transferred to another cache, and that's going to be a too complex process, so it becomes a complex in maintaining the consistency. So there is scalability limit as the number of CPUs increases, synchronization becomes harder and harder, so it grows exponentially as the number of CPUs increase. This complexity of synchronizing them becomes exponentially harder. So overall, what you can see that features the asymmetric and symmetric, if you look at it, the processor roles, it's a master slave in terms of symmetric. All processors have equal rights in the symmetric. Operating system runs on master CPU only in case of symmetric, whereas all CPUs can run operating system. There is no load balancing possible in the symmetric, but yes, load balancing is possible in symmetric. No fault tolerance in symmetric type of multiprocessing, but in symmetric multiprocessing, load tolerance is far better. And use cases for asymmetric is embedded systems, real-time systems, whereas for system asymmetric things, general purpose multi-core CPUs and all. So that's about asymmetric and symmetric multiprocessing systems. Thank you. Hi friends, welcome back. Now let's get into our next session. The next session is about multi-core processors. With the improvement in the VLSI technology, the enhancement in the VLSI technology, the size of the chip started shrinking, and the physical dimension of the chip cannot be reduced as the logical size of the chip was shrinking, because it has to be handled manually or by the even robots also. It should be of some dimension that can be handled. And due to advancement in the VLSI technology, the size of the processor went on shrinking, and this created void in the physical chip inside, and this void could be filled with more number of processors, and this idea gave birth to multi-core processor. A multi-core processor is a single physical CPU chip that contains two or more independent processing units called cores. So this example, we can see that two processors are put on the motherboard. One is processor 0, other is processor 1, and each processor is in turn having two cores. Each core has its own associated L1 cache, and there is L2 cache per processor. So totally in all, each processor chip will contain two cores, two L1 cache memories, one for each core and one L2 cache. So that way, if our motherboard contains two processor chips, then in all we have 4 cores, 4 L1 cache memories and 2 L2 cache memories, and that through the motherboard is connected to main memory and other associated system. So why to use multi-core processor? The first thing is power efficiency. So it requires lower power than multiple CPUs. Instead of having one CPU per chip and each chip is consuming power, we can make one chip having multiple cores, and that chip will consume almost same power as a chip containing a single CPU. So that's one advantage. That's power requirement will be very small. Then we can run the task parallelly, so multiple tasks can be run simultaneously because each core can take up one task individually. And then space we can save, and because the improvement in the VLSI technology, the size is shrinking, and because of this, in the available space we can have more number of cores. Then considering separate chips, one containing each processor, if one chip contains 4 processors, then the overall size required in the motherboard is of one chip instead of size of 4 chips. So that if we just keep looking at that, then these benefits grow multifold one by one, and then we have a better performance scaling than increasing the clock speed. So there was a limit to the clock speed. We went on increasing the clock speed from 3 MHz 8085 processor till went on to 3 GHz, and later we realized that beyond 3 GHz, if we go, the processor started getting heated and lot of problems were arising. The computational problems were arising, the heat dissipation problem was arising, power requirement problems were arising. So we tried to stop increasing the processor speed. Luckily by that time improvement in the VLSI technology was giving us more space, So we could think of adding more cores than increasing the clock speed. So through adding more cores, we used to get a higher performance than what we were doing earlier by increasing the clock speed. Now, how does the operating system works with a multi-core CPUs? So here the operating system sees each core as a separate processor. So it's like CPU 0, CPU 1 and so on. Then uses this multiprocessor scheduling to assign tasks across the cores. Then threads can run simultaneously on different cores. Operating system uses load balancing, process affinity and core specific queues to manage the performance. Now if we think of what a multi-core processor can do, so let's just check up one example. Let's core can work with a single thread or multiple thread. That's how the processor can be designed. So here a single threaded processor core, what happens? So when we have a code to compute, it takes a computation, but whenever we need data from the memory, we need to access the memory, then we have a memory stall cycle. So when the data is exchanged between memory and the processor, then again computation continues. Then whenever memory help is required, then the processor used to stop and wait for the data to come in and write or read, then again. So this was single thread operation. It works with a compute thread, compute cycle, memory cycle alternately. So instead of that, if we could create a two-thread processor core, then when one thread is working with a memory, the another thread could be working with a computation. So we can interleave these computation and memory cycles, so that any time if you look at it, either at thread 0 or at thread 1, one computation is going on. So the first part, thread 0 is computing, second part thread 1 is computing, third part thread 0 is computing, then thread 1, then thread 0, thread 1, thread 0, thread 1. So if you look at it, then the process will never stop, whereas in the previous case the process was coming to an halt whenever a memory access is required. So whenever memory access is required, that time the thread continues to wait for the memory. By that time another thread takes up the next task, continues the work, and when the next thread needs memory access, then the first thread comes back and takes the control and continues. So this way we can see that every slot there is one computer cycle, and hence the computation goes faster. So in all, what is happening here is one CPU's core has two threads, and because of this the process has speed up 2 times. So if we take an example, UltraSpark TI CPU, it has got 8 cores per CPU per chip, and each core can have 4 hardware threads. So 8 cores per chip, and each core can have 4 hardware threads. That means in all we can think from the outside world perspective that UltraSpark TI, this processor is equivalent to 32 logical processors. That means in parallel it can run 32 processes or 32 threads simultaneously, because there are 8 cores in one chip and 4 hardware threads are there per core. So that makes 32 logical hardware threads in this CPU. So from the outside world it appears as if 32 are being run simultaneously. The next session on the process management. Now we come to an interesting topic, virtualization. So what virtualization is, why it is important, and how scheduling comes into picture, all that is what is our next items to discuss. So let's imagine a situation where we have one system and there are multiple users, and each user having multiple tasks. So in all we have one system one system means it is working with one CPU, that is one type of CPU, one brand of CPU, and on that the system is working with one operating system, and we have multiple users, and each user may have many tasks, and the problem comes when all the tasks may not be comfortable with the same operating system which is currently working with that particular system. And to aggravate the problem, we have another issue that all tasks may not be compatible with the same CPU type. So in all, what is happening is we have one CPU, on that there is one operating system, and we have many users. Each user may be working with many tasks, and the problem with each task may want to work on different operating systems. Each task may want to work on different type of CPU. Then what is the solution? What is the solution? The one positive side of this is we are talking with the human users. We are talking with that whose response time is quite slow compared to the machine's response time, and hence multitasking can be taken up. But only issue here is each user, each task may want a different type of CPU to be used. They want to use different type of operating system to use, and that is where a simple multitasking cannot help us here. Then what we can do, let's see. So what we have with us, we have one hardware that we can't change. That is what we have with us. That is one type of CPU we have. It may be Intel CPU, it may be AMD CPU, it may be Android, or it may be iOS, whatever CPU we have. Yes, we have one. Then it is working with one operating system. It may be Windows or Linux or whatever, don't know. Yes, it is the system we have, and that system has got a hardware, that is processor and other peripheral devices. Yes, it has come with it. So we just can't keep changing them as per the request of the users, as per the requirements of the task and all that, but we need to find out some way out, and that's what we are now into. So what we can do now is we can create one more layer on this, what we call is hypervisor, and this hypervisor hides all the lower layers. That means it hides the operating system from the users, it hides the operating system from the task, it hides the hardware underneath from the users, it hides the hardware underneath from the task. So this is creating an illusive environment that what you want we have. So that creates an illusion that we have a machine which is what you wanted. Say user 1 wanted one type of machine, then yes, we say that we have that machine. That means it is using the CPU what user 1 wanted. But in fact, the actual CPU what is available with the system may not be the same as the CPU which the user wanted. But yes, we can somehow convince the user that we have the same CPU what you wanted. So what we need to do, this hypervisor has to act like a translator, the language of the CPU which is actually present. So let us call it the physical CPU. So it should act like a converter, translator from the language of the physical CPU and the language of the virtual CPU, that is, which doesn't exist, but for the user it looks like it is existing. So we have created a virtual environment saying that whatever you wanted, we do have that. So in that, what we can do in this what we call virtual machine, we can say that which CPU you want, yes, we do have. Which operating system on which you want to work, yes, we do have. So this hypervisor acts like a translator between the two ends. So user wants one type of CPU, we have one type of CPU in reality. So virtual CPU, real CPU, there is translation required. Yes, we are doing through hypervisor. Then we have CPU, an operating system which is installed physically on the system, and the user wants some other operating system. Then instead of saying no, let us say that you have your own operating system with us, so nothing to worry. So we create an environment as if the whole system is working on that particular operating system. That means this virtual machine will consist of one virtual processor and another operating system, which is not the one which is there here. So to differentiate this, let us give some nomenclature to that. The actual CPU available with the system, let us call it physical machine, and the one which we have created as an illusion to the user, let us call it virtual machine. The physical machine consists of one type of CPU, and the physical machine comes with one type of operating system installed, and under the virtual machine we have a translator that translates between the language of the physical CPU and the virtual CPU. And as in case of operating system, let us call it this, we can't call it physical one, so let us call it host operating system, and the operating system which the user wants, so let us name it as a guest operating system. So let us assume that we wanted two different environments, so two different environments are created in which the virtual machine 1 VM1, virtual machine 2 VM2, so the two environments are created, and let us assume that VM1 works on one type of CPU and VM1 wants one type of operating system. So we have a virtual processor under VM1, and we have one guest operating system in VM1. Same way under VM2 we have one virtual processor and one guest operating system, and below the hypervisor we have the host operating system and the physical processor. So on top of that we have users, tasks and all that which interact with these virtual machines. So this is the concept of virtualization. So let's see what a virtualization is as a definition. So it is one which has a common hardware. We have multiple users. Each user wants to work on a different hardware, maybe Intel, AMD, Texas Instruments, NVIDIA and all that, and each one wants to work on different types of operating system, maybe Linux, Windows, Unix, his or her own choice. So the traditional ones says that there is one hardware, there is one operating system, on that we have applications, but our virtual architecture says that there is one hardware, on that there is a virtualization layer. On top of that, each virtual machine has got its own operating system. So for each user it appears as if working with one thing, that the whole system is their own, and other thing is working on their own liked environment and all that. So that's the advantage of working with virtualization. So here the virtualization is the process of creating virtual version of something like hardware, operating system or storage. Multiple isolated environments called virtual machines, or in short we call it VMs, can run on a single physical machine. That's what we just wanted earlier. And the software that enables all these activities to take place smoothly is what we call a hypervisor or virtual machine monitor, so in short VMM. So here this gives a better picture of what we are talking about. So we have a shared hardware resources on the bottom, then we have a hypervisor, and then we have a guest operating system, and on top of that applications are running. That is, application means the tasks are running. So this talks about one user or multiple users. So various tasks are running through API calls. So they interact with their guest operating system. The guest operating system will interact with the hypervisor, and hypervisor in turn will interact with the shared hardware resources like shared memory, shared CPU and all that. So that's virtualization. And then coming to virtual scheduling, we have multiple tasks, and multiple tasks want to work on different types of machines, different types of operating systems. So this whole thing has to be somehow scheduled. So there are basically two types of scheduling required. One is the virtual machine scheduling, and the other one is the task scheduling. So multiple virtual machines share the same physical CPU. Each virtual machine thinks that it has its own CPU or no CPUs. Hypervisor must schedule the CPU time across all the virtual machines. Inside each virtual machine, the guest operating system must schedule tasks for the processes or the threads. So what we have, it's a double complicated, that at one side we have a set of virtual machines working, and that virtual machines should be allotted CPU time, that is a physical CPU time. So that is done by the the hypervisor scheduling, and inside each virtual machine the guest operating system must take care of scheduling the processes or threads. So this process scheduling, thread scheduling and all we have seen earlier, it is same as what we discussed earlier. This is at one operating system and there are multiple processes and they are working on that. So that is then we have two levels of scheduling: the virtual scheduling by hypervisor and process or thread scheduling inside the virtual machine. So that's what we have seen now. So hypervisor scheduling schedules the virtual machines and the guest operating system schedules the task inside that. So that's hypervisor schedules entire VMs on the physical CPUs. Guest operating system schedules threads or processes inside that virtual machine, and the hardware executes what is assigned by the hypervisor. It doesn't know anything about the guest operating system. The hardware doesn't have any information about how many users are there, how many processes are there, how many threads are there. Nothing. Everything is hidden from the hardware. The hypervisor is assigning all these things, so it is the duty of the hypervisor to maintain the fairness and all details about scheduling. So types of virtualization scheduling: the space scheduling. Each VM gets exclusive access to core of a time slice. Time sharing, it is time multiplexed. Fair scheduling, that is share CPU time equally based on weights. Then real-time scheduling is reserved CPU's resources for critical virtual machines or tasks. So the challenges what we find in virtualized scheduling is double scheduling problem. Guest operating system may think a thread is running, but hypervisor might have paused the whole virtual machine. So that is one problem, because finally hypervisor has to allow one virtual machine to get the access of the CPU, and the guest operating system has allotted one thread or a process to run, but the whole virtual machine is paused by the hypervisor. Therefore the guest operating system doesn't know that it is not working. Then the performance interference, one VM may slow others down, noisy neighbor problem and all that. Timekeeping is another problem. Virtual CPUs need special support for accurate clock timers. And fairness and priority. So maintaining balance between fairness and the priority is a big problem when we work on virtualized system. So friends, that's it in the second module. Please have anything to know more, please contact me on the given addresses, and please do like, share, comment, and please subscribe to the channel. Thank you.